Hello there, and welcome to Science for Sleep, where curiosity gets comfortable, ideas move gently, and even the strangest corners of physics are invited to slow down for the evening. Tonight, we're setting our attention on a question that sounds simple at first and then becomes wonderfully inconvenient the longer you think about it. Does time move faster in space? It is the sort of question that can arrive quietly in the mind, maybe while looking up at the night sky, maybe while seeing a photograph of astronauts floating above Earth, maybe while noticing that the stars seem calm, even though nearly everything out there is moving at extraordinary speed. You might wonder whether clocks behave the same way up there, whether seconds in orbit feel like seconds in your kitchen, whether a person who leaves Earth and returns comes back with the same amount of time as everyone who stayed home. The short answer, rather surprisingly, is no. Time does not behave exactly the same everywhere. That may sound like the beginning of nonsense, but it is instead the beginning of modern physics. For most of daily life, time feels dependable. A minute is a minute. 10 minutes waiting for toast can feel longer than 10 minutes on holiday, of course, but emotionally unfair timing is a separate issue. Your watch appears loyal. The clock on the wall keeps moving forward. Morning becomes afternoon. Tea becomes cold. Emails become more numerous. Everything seems consistent enough. Yet beyond everyday experience, nature is less rigid than it first appears. If you move very quickly, time changes. If gravity becomes stronger or weaker, time changes. If you rise high above Earth, even by a modest amount, time changes. And if you travel near something extremely massive like a black hole, time changes so dramatically that the whole idea of a shared schedule begins to collapse into chaos. So tonight, we'll explore why that happens. We'll do it calmly, step by step, without requiring a chalkboard, a PhD, or the ability to enjoy equations before bed. Before we begin properly though, I'd love to know where in the world you're listening from tonight and what time it is there right now. A fitting little question perhaps. Somewhere, someone is hearing this in bright morning light. Somewhere else, another listener is wrapped in midnight quiet. In one city, trains are beginning their routes. In another, dishes have been washed and lights turned low. All of us sharing the same conversation while standing in different slices of the clock. And even that ordinary fact hints at something deeper. We already live with multiple versions of time. Time zones, schedules, calendars, deadlines, jet lag, birthdays, late buses, early alarms. Human life is organised by time so completely that we rarely pause to ask what time actually is. We mostly ask what time it is now, which is practical, fair enough. If you find this evening's journey soothing, interesting, or simply a pleasant way to unwind after a long day, I'd be very grateful if you liked the video, subscribed, or returned for future wanderings through science at a slower pace. It helps this quiet little corner reach others who might need a thoughtful place to land for a while. Now then, settle in. Let your shoulders drop a little. Let the day loosen its grip. There is no rush here. We're going to talk about clocks, satellites, astronauts, gravity, motion, and one of the most surprising discoveries humanity ever made, that time is not the fixed background we once believed it to be. For centuries, people assumed time was universal. One invisible river flowing the same way for everything and everyone. It didn't matter whether you were standing still, riding a horse, crossing an ocean, or dropping an apple from a tree. Time was thought to pass evenly, everywhere. That assumption feels natural because it matches ordinary life. If two friends meet for lunch, they do not worry that one of them aged more quickly on the walk to the cafe. If a baker sets a timer for 20 minutes, the cake does not question the philosophy of duration. If a train departs at noon, passengers expect noon to mean the same thing for everyone on the platform. And for slow speeds and weak gravity, those assumptions work beautifully. They work so well, in fact, that humanity built civilizations on them. We organised markets, we timed harvests, we rang bells, we built railways, we standardised cities, we invented watches, clocks, calendars, and the deeply suspicious phrase, just 5 more minutes. But nature was quietly keeping a secret. Once measurements became more precise, and once scientists began studying light, motion, electricity, and the structure of the universe more carefully, the old picture started to wobble. The wobble became a revolution in the early 20th century when Albert Einstein proposed something astonishing. Time was not absolute. It was linked to space itself. It could stretch. It could slow. It could differ from one observer to another depending on motion and gravity. This was not poetry. It was mathematics backed by evidence. And later, it was tested again and again. Today, these strange effects are not just theoretical curiosities discussed in quiet rooms full of coffee cups. They are built into the technology many people use every day. Your phone's map system depends on clocks in satellites. Those clocks tick differently from clocks on Earth because of both speed and gravity. Engineers must correct for those differences constantly. If they did not, navigation errors would grow quickly. So the answer to our title question is already woven into modern life. Does time move faster in space? Sometimes yes, sometimes no. It depends where in space, how fast you're moving, and what nearby gravity is doing. That may sound frustratingly conditional, but physics is often like that. We ask a dramatic question and receive a calm answer beginning with, well, it depends. Still, that dependence is where the wonder lives. Imagine an astronaut orbiting Earth for months. When they return, they have experienced time very slightly differently from people on the ground. Not enough to notice by feeling it. Not enough to return dramatically younger with a new haircut and mysterious wisdom. But enough that precise instruments can measure it. A person in orbit and a person on Earth do not age at exactly the same rate. That sentence remains one of the most delightful examples of reality ignoring our instincts. Or picture a future spacecraft travelling at a large fraction of the speed of light. Time for those aboard could pass much more slowly relative to people back home. They might journey for a few years and return to find decades passed on Earth. This is not magic. This is relativity. And somewhere between those tiny satellite corrections and those grand interstellar possibilities lies the real story of time in space. We'll also need to untangle a common misunderstanding. When people hear that time slows down or speeds up, they often imagine a person noticing their own wristwatch behaving oddly. But that is not how it feels from the inside. Your own heartbeat, thoughts, and clock all remain normal to you. You never sense your personal time dragging like a sleepy afternoon meeting. Instead, differences appear when comparing clocks that follow different paths through motion and gravity. That distinction matters, and we'll return to it often. Because relativity is not about feeling strange. It is about measurement revealing that the universe is stranger than feeling alone would suggest. There is something almost comforting in that. Our senses are useful, but incomplete. The stars do not twinkle because they are tiny candles. The ground does not feel like it spins, yet Earth rotates rapidly. Solid objects are mostly empty space at the atomic level, and time, the most familiar companion of all, turns out to be flexible under the right conditions. Even so, don't worry. We're not going to disappear into technical fog tonight. We'll move carefully. First, we'll understand what physicists mean by time in the first place. Then we'll see why there is no universal master clock hidden behind the sky. After that, we'll meet Einstein's two great insights. Motion changes time, and gravity changes time. We'll visit satellites, astronauts, the moon, Mars, and black holes. We'll ask whether future time travel is possible in a scientific sense, and along the way we'll keep returning to the same humble question. What is a second, really, if different places and paths can disagree about it? There is also a quietly human side to this subject. We treat time as a possession. We save it, waste it, lose it, spend it, run out of it, and promise to make it up later. We apologize for being late as if we personally damaged the universe. We celebrate dates. We count years. We set alarms against our better judgment, yet physics invites another perspective. Time may be less like a universal currency and more like part of the geometry of reality, something woven into existence itself, responsive to speed and mass, measured locally rather than imposed globally. That sounds grand, but it reaches into ordinary life. Even now, as you listen, clocks at sea level and clocks on mountains tick at slightly different rates. The difference is tiny, but real. The universe is doing relativity everywhere, all the time, whether or not anyone is paying attention. And perhaps there is something soothing in that too. The cosmos is not rigid and mechanical in the old sense. It is subtle. Context matters, position matters, motion matters. Two clocks can both be correct and still disagree. Many arguments could learn from this. As the evening settles further, maybe notice your own relationship with time right now. Has today felt quick or slow? Did the morning vanish? Did an awkward 5 minutes last a century? Psychological time bends in the mind while physical time bends in the universe. We contain both experiences at once, emotional duration and measurable duration, one governed by attention, the other by relativity. And soon we'll begin separating those two threads. For now, simply rest in the question. Above Earth, high beyond weather and rooftops, instruments circle the planet carrying clocks. Those clocks do not keep exactly the same time as the ones beside roads, bedsides, ovens, train stations and office walls below. Somewhere over the horizon, another second is arriving differently. Now that we've asked whether time moves faster in space, it helps to pause and sort out a more basic issue first. What do physicists actually mean when they use the word time? Because outside science, time is many things at once. It is the reason dinner gets cold. It is the number beside a meeting reminder. It is birthdays, deadlines, late trains, growing older, healing, waiting, rushing, and saying, "Where did the week go?" It is emotional, practical, personal, and often mildly annoying. But in physics, time must be handled more carefully. A physicist cannot write an equation using that long afternoon at work as a unit. However accurate it may feel, it lacks consistency. Science needs something measurable, repeatable, and shared. So when physicists talk about time, they usually mean a quantity that allows events to be ordered and durations to be compared. That sounds dry at first, but it is actually profound. Time in physics is a way to answer two essential questions. What happened first? And how much separation was there between events? If a star explodes before its light reaches a telescope, order matters. If a particle survives for 1/1,000,000th of a second before decaying, duration matters. If a spacecraft sends a signal and receives a reply later, intervals matter. Without time, physics loses sequence. Without sequence, cause and effect become very hard to organize. So, in one sense, time is the parameter that lets the universe have stories instead of random snapshots. Imagine the world with no time at all. There would be no before toast and after toast, no seed becoming a tree, no rain beginning and ending, no sentence unfolding word by word. Everything would simply be frozen states, with no change connecting them. Physics is deeply concerned with change, and time is how change is tracked. That is why many equations include it. Position changes with time. Velocity is change in position over time. Acceleration is change in velocity over time. Radioactive decay happens over time. Orbits unfold over time. Heat spreads over time. Even boredom during slow meetings appears to expand over time, though that remains a personal rather than official unit. Still, saying time measures change creates another puzzle. Do we need time first in order to describe change, or do we infer time because things change? That question has occupied philosophers and scientists for centuries. Some thinkers argued time is fundamental, existing whether or not anything happens. Others argue time is just our way of describing relationships among changing things. Physics has historically used both attitudes depending on context. For everyday mechanics, time behaves like a dependable background coordinate. For deeper theories, things become less settled. Let's start with the practical version. Suppose you toss a ball upward. You can measure where it is after 1 second, 2 seconds, 3 seconds, and so on. Time acts like a ruler, except instead of measuring distance through space, it measures progression through events. That analogy is useful but incomplete. A ruler in space can be placed beside an object. Time cannot be held next to a Tuesday. We never touch time directly. We observe clocks, motion, decay, oscillations, rotations, heartbeats, pendulums, and atomic transitions. Time is inferred from regular processes. That means clocks are central to physics, not because clocks create time, but because clocks provide repeatable change we can count. This distinction matters. A clock is not time itself. A clock is a device that undergoes predictable cycles. A pendulum swings. A quartz crystal vibrates, Earth rotates, an atom transitions between energy states. By counting these repeating processes, we label durations. So when someone asks, what time is it? The hidden meaning is closer to, how many agreed upon cycles have passed since our chosen reference point? Which sounds less elegant at dinner but more accurate. Take a second, for example. Many people imagine a second as a natural tiny chunk of time floating around in reality. In practice, a second is defined using atomic behavior. Modern standards use a specific number of oscillations of the cesium atom. That means the unit of time is anchored to matter behaving reliably, not to sunrise, not to moods, not to whether lunch felt brief. This precision became necessary because older methods were not stable enough. Earth's rotation, though useful, is not perfectly constant. Planets are good companions but imperfect metronomes. Atoms turned out to be better, so physics refined timekeeping by tying units to the most dependable regularities available. And yet, even with excellent clocks, a deeper question remains. Is time something that flows? Everyday language suggests it does. We say time passes, time flies, time drags, time slips away. We imagine ourselves carried along by a current. But physics is more cautious with that language. Equations generally do not require a mystical flowing substance called time. They require order, intervals, and relationships between measurements. In classical physics, time often appears as a parameter t, a symbol in equations. Plug in one value, the system is here. Plug in a later value, the system is there. That may sound disappointingly plain, but it was enormously powerful. With it, scientists predicted falling objects, planetary motion, pendulums, projectiles, tides, and machinery. Time served as the common stage on which events unfolded. Then came relativity, where our calm little stage began moving the furniture. Before we reach that revolution, it helps to understand one more classical idea. In older physics, time was assumed to be universal. If two observers had good clocks, they could in principle agree on durations and simultaneity once synchronized properly. If lightning struck two towers at the same time, everyone could agree it was simultaneous. If two bells rang 1 minute apart, everyone could agree on the interval. That assumption seems obvious, because human life operates comfortably within it. Yet it turns out to be only approximately true. At low speeds and modest gravity, universal time works well enough. At cosmic extremes, it does not. This is where physicists become very specific about wording. They often distinguish between coordinate time and proper time. These terms sound like they belong in a strict boarding school, but they are useful. Coordinate time is a time label assigned within some chosen reference system. It helps compare events across a map of space and time. Proper time is the time actually measured along a specific path by a clock travelling with an object. That second one is deeply important. Your wristwatch measures your proper time. An astronaut's onboard clock measures the astronaut's proper time. A satellite clock measures the satellite's proper time, and these need not match after different journeys. This is one reason asking what is the real time becomes tricky in relativity. Different observers may each have valid measurements. That sounds unsettling only because we grew up expecting one master answer. Nature appears comfortable with multiple local answers. There is something almost democratic about it. Each clock reports honestly from where it has been. To make this concrete, imagine two identical clocks. One remains on Earth. One travels quickly in space and returns. When compared, they may disagree slightly. Neither clock malfunctioned, neither cheated. They simply followed different paths through the universe. That idea would have seemed absurd in earlier centuries. Today it is experimentally confirmed. So in modern physics, time is not merely what clocks measure in the old circular joke. Rather, clocks reveal how duration depends on motion and gravity. And that means time is connected to geometry. Not geometry in the schoolbook sense of triangles waiting quietly on paper, but geometry of space-time, the structure within which events occur. We'll get there soon. For now, another useful point. Physicists often treat time differently in different theories. In Newtonian mechanics, time is absolute and external. In relativity, time is woven with space and depends on the observer's motion and gravitational environment. In quantum mechanics, time often reappears as an external parameter again, which creates tension with relativity. This tension is one reason unifying physics remains difficult. Space and time are not handled identically by all our best models. Even experts continue debating what time fundamentally is. So if you have ever felt uncertain about time, you are in distinguished company. Some of the brightest minds in history joined you there. Now, despite all this complexity, we should not lose the ordinary meaning entirely. Human beings experience time through memory and anticipation. We remember the past. We expect the future. We act in the present. Physics measures intervals, but psychology feels them. These are related yet different subjects. An hour in a dentist waiting room and an hour at a holiday meal are physically equal by clocks, yet emotionally suspiciously unequal. Science can discuss both, but tonight our focus is physical time, measurable duration, and event order. Still, the human side explains why time fascinates us so much. It is both a scientific quantity and the medium of our lives. We age in it, we plan within it, we regret and hope through it. That emotional weight can make scientific time feel stranger when it refuses to behave simply. Imagine learning that clocks on mountains run differently than clocks at sea level. The practical difference is tiny, yes, but conceptually enormous. The thing we trusted most to be universal turns out to vary. Even language struggles with this. We ask whether time moves faster in space, but in physics it is often better to ask whether one clock accumulates more elapsed time than another under certain conditions. Less catchy for a video title, admittedly, yet more precise, and precision is how physics advances. Not by removing wonder, but by sharpening questions until reality can answer them clearly. So what do physicists mean by time? They may mean a coordinate used to label events, a measurable interval shown by clocks, a variable in equations describing change, a local duration along an object's path, a dimension linked with space, a concept still not fully understood at the deepest level. Quite a lot for one short word. No wonder it carries so much confusion. There is also a subtle comfort here. We do not need a final theory of time to use it productively. Sailors navigated with imperfect clocks. Engineers built railways before relativity. You can bake bread successfully without solving space-time geometry. Understanding can deepen while daily life continues. The universe allows both mystery and breakfast. As the night grows quieter, consider the clock nearest to you. Perhaps one glows softly from a bedside table. Perhaps numbers rest on a phone screen. perhaps there is only the vague sense that it is late enough to be listening to discussions about relativity. Whatever form it takes, that clock is counting regular change and translating it into something your life can use. Yet somewhere above Earth, atomic clocks in satellites are counting too, and not at quite the same rate. That difference only makes sense once we let go of the old idea that time is one universal background shared equally by all. If time is measured locally and tied to clocks, then whose clock sets the universe? It is natural to imagine that somewhere, hidden behind stars and galaxies, there must be one master clock, a grand cosmic device ticking steadily for everything. Perhaps mounted invisibly behind the universe like a thermostat nobody can find, each second passing once everywhere for all things alike. It is a comforting image, orderly, clean, efficient, very suitable for office management, and it is also wrong. Modern physics tells us there is no universal cosmic clock keeping time for the entire universe in one shared way. No single now spreads across all space. No master second arrives simultaneously for every planet, every spacecraft, every galaxy, every drifting atom. Instead, time is local. It is measured where you are, by the path you take, under the conditions you occupy. That idea can feel slippery at first because daily life trains us otherwise. You probably woke according to a clock that seemed objective enough. Perhaps you checked the hour on a phone. Perhaps a bus arrived late according to a schedule, proving time exists mainly to disappoint commuters. Perhaps lunch happened at a named hour and sunset at another. All of this creates the impression that time is universal and shared. Yet what is actually shared in ordinary life is not fundamental cosmic time. It is synchronized human convention under conditions where relativistic differences are tiny. That distinction is everything. Let's begin with the simpler world we know well. Within one city, clocks can be synchronized fairly easily. Signals move quickly enough, distances are small enough, speeds are slow enough, gravity differences are modest enough. If two clocks disagree noticeably, we assume one needs fixing rather than rewriting physics. This works because everyday environments hide the deeper structure of time. Nature is being polite, but stretch those distances, increase those speeds, change the gravitational environment. Suddenly the hidden complexity steps into view. To understand why no cosmic clock exists, we need to ask a deceptively simple question. What does it mean for two distant events to happen at the same time? Suppose one star explodes in a galaxy far away, while here on Earth someone drops a spoon in a kitchen. Did those happen simultaneously? Your instincts may say the question has a definite answer waiting somewhere. Physics says, not absolutely. To compare distant events, information must travel. Usually that means light, but light takes time to cross space. A signal from the moon takes a little over a second to reach Earth. From the sun, about 8 minutes. From nearby stars, years. From distant galaxies, far longer than civilizations usually keep receipts. So when we observe remote events, we're always seeing the past. You never see the sun as it is right now. You see it as it was several minutes ago. You never see a nearby star as it is tonight. You see earlier light arriving tonight. Already, the notion of one universal present becomes troublesome. The universe does not hand us a synchronized live broadcast. It sends delayed messages. Perhaps we could still imagine an invisible cosmic authority who knows the true simultaneous present even if we do not. That was closer to older thinking. Then Einstein complicated matters magnificently. Special relativity showed that simultaneity itself depends on the observer's motion. This is one of the most important and least intuitive discoveries in science. Two events judged simultaneous in one frame of reference may not be simultaneous in another moving frame, not because someone made a mistake, not because signals were delayed badly, because the structure of space-time itself does not preserve a universal shared now. Let's picture a train, since trains have generously served physics thought experiments for years without consent. Imagine lightning strikes both ends of a very long train at what a person standing on the platform considers the same moment. Light from both strikes reaches the platform observer together, so they conclude the strikes were simultaneous. Now imagine someone inside the train moving toward one flash and away from the other. Light from the front strike reaches them sooner than light from the rear strike. Using the rules of relativity, that observer concludes the strikes were not simultaneous. Both observers are valid within their frames. There is no hidden cosmic referee blowing a whistle and announcing who got true simultaneity. That whistle was retired. This means there is no universal slicing of the universe into one shared present moment. What counts as now here does not map uniquely to now somewhere far away. That is difficult only because language encourages us to think otherwise. We say, what is happening right now on Mars? The practical meaning is clear enough, but the fundamental meaning depends on how we define synchronization between Earth and Mars, including relative motion and signal timing. Even between nearby planets, now requires conventions. Across galaxies, it becomes far more ambiguous. So the first reason there is no cosmic clock is relativity of simultaneity. Different observers moving relative to one another do not share one universal present. The second reason involves gravity. General relativity tells us gravity affects time itself. Clocks in stronger gravitational fields tick more slowly relative to clocks in weaker fields. That means a clock near a massive body and a clock far away do not accumulate time identically. Which one is the master clock? Neither. Each measures proper time along its own world line, meaning its own path through space-time. A clock on Earth's surface, a clock aboard a satellite, a clock near Jupiter, a clock drifting in interstellar space. All legitimate, all local, none globally supreme. This can be unsettling because we're used to ranking clocks. We ask which one is correct. Physics answers with unusual calm. Several can be correct and still disagree. That sentence alone deserves a quiet moment. Two clocks can both work perfectly and yet record different elapsed times because they experience different motion and gravity. No defect required, no battery issue, no passive-aggressive tampering, just reality. Consider GPS satellites. Their clocks run differently from clocks on Earth. Engineers must account for both special relativity from orbital speed and general relativity from weaker gravity higher above Earth. If there were one cosmic clock, satellites could simply obey it. Instead, practical systems rely on careful conventions, corrections, and reference frames. Modern navigation quietly depends on the absence of universal time. There is also a cosmological angle. You may hear scientists speak of the age of the universe, around 13.8 billion years. That sounds suspiciously like a universal clock after all. But even here, nuance matters. Cosmologists often define a useful time coordinate tied to the large-scale expansion of the universe and observers moving with the average cosmic flow of matter. This is sometimes called cosmic time in specific models. It is extremely useful. It is not a metaphysical master clock governing all circumstances. Observers moving rapidly relative to that flow, or living in very different gravitational environments, can experience different elapsed proper times. So even the age of the universe is subtle. There are coordinate systems that help describe cosmic history, but coordinates are tools, not divine wristwatches. Think of maps. A map grid is useful. It helps locate cities. But the grid lines are not painted onto Earth by nature. They are human structure imposed for clarity. Likewise, time coordinates can organize physics without being universal flowing substances. Another reason people expect a cosmic clock is psychological. Human consciousness seems to move through moments. We feel a present. We remember a past. We anticipate a future. This inner experience suggests the universe itself must possess one advancing now. Yet physics does not require that feeling to be fundamental. Our brains create coherent temporal experience from local processes, memory formation, sensory updates, prediction, bodily rhythms. Useful, yes. Universal, no. The cosmos need not feel like our nervous system, and frankly, that is probably for the best. If galaxies shared human scheduling instincts, there would be endless delays. Now let's examine what replaces the cosmic clock idea. Instead of one universal time, relativity gives us space-time and world lines. Every object traces a path through space-time. Along that path, a clock measures proper time. This is the object's own elapsed duration. You have one. A satellite has one. A photon is stranger, and we'll leave that complication politely aside for now. The important point is that elapsed time belongs to paths, not to the universe as one synchronized whole. This is elegant once it settles in. Reality does not need one central ticker. Each traveller carries their own measure of duration. That sounds almost personal, though it is rigorously physical. Imagine two hikers starting together, taking different routes over mountains, and meeting again later with different step counts. No contradiction exists. Different paths produce different totals. Relativity says something similar with time. Different journeys through motion and gravity can yield different elapsed durations between reunion events. So asking for one universal cosmic time is a bit like asking for the single true number of steps for all possible hikes between two cabins. The question assumes more uniformity than nature provides. Historically, the dream of universal time made sense. Newtonian mechanics worked brilliantly with absolute time as a background parameter. For slow speeds and common scales, it remains an excellent approximation. We still live mostly inside that approximation. Clocks on opposite walls behave nearly alike. Friends age nearly equally after lunch. Buses fail for reasons unrelated to relativity. Everyday life remains manageable. But approximation is not ultimate truth. Flat Earth maps work locally without making Earth flat. Likewise, universal time works locally without making time universal. There is a quiet lesson in that. Human intuition evolved for practical survival, not for cosmic precision. We needed to throw spears, not reconcile simultaneity across galaxies. We needed to notice dusk, not derive Lorentz transformations. So it is no insult to instinct that relativity feels odd. Instinct was solving different problems. Even language struggles once cosmic clocks disappear. Phrases like, right now in another galaxy, become shorthand rather than exact statements. We can define reference frames and coordinate systems to make them meaningful, but no observer-independent cosmic now comes included. And yet, this lack of universal time does not create chaos. Physics remains predictive because laws are written to work consistently across frames. Observers may disagree on time intervals or simultaneity, but they agree on deeper invariant structures. That is one of relativity's great achievements. It replaced naive certainty with more sophisticated consistency. A less rigid universe, yet a more coherent one. There is something soothing in that too. The world need not be simple to be lawful. As evening deepens, perhaps picture millions of clocks, kitchen clocks, wristwatches, laboratory clocks, atomic clocks in satellites, oscillations in atoms, pulses from pulsars, rotations of planets, biological clocks in cells. None of them commands the others. None sits on a throne above Andromeda issuing seconds to the cosmos. They measure time where they are according to their circumstances, local rhythms inside a shared reality. And if there is no universal cosmic clock, then the next question becomes irresistible. If old physics once trusted absolute time, how did that belief become so powerful in the first place? Long before astronauts carried atomic clocks into orbit, before satellites corrected their timing thousands of times a day, before relativity bent the confidence of earlier centuries, there was a picture of the universe so powerful and so successful that it shaped science for generations. In that picture, time was absolute. It flowed evenly, steadily, and identically for everything, no matter where you were, no matter how fast you moved, no matter what planets spun overhead. Seconds passed the same way for apples, oceans, cannonballs, moons, merchants, and philosophers trying to look serious in portraits. This was the universe of Isaac Newton. To understand why modern ideas about time felt so shocking, we first need to appreciate how convincing Newton's older framework was. Because it was not foolish, it was brilliant. It explained the world with such accuracy that it became the foundation of physics, engineering, astronomy, and practical life for centuries. And within that grand system, time occupied a special role. It was the fixed background against which everything else moved. Imagine a stage in a theatre. Actors walk, speak, fall, argue, and exit dramatically. Props are moved. Scenes change. But the stage itself remains in place beneath the performance. For Newton, space and time were something like that stage. Objects moved through space. Events unfolded in time. But space and time themselves were not affected by the drama. They simply existed, steady and universal. Newton expressed this view in language that still sounds striking today. He described absolute time as flowing equably by its own nature without relation to anything external. That is a formal way of saying time keeps going whether or not anything notices. If the universe were empty, time would still pass. If all clocks broke, time would still pass. If no one remembered birthdays, time would still pass, though cake sales might suffer. This concept matched intuition remarkably well. After all, in ordinary life it seems obvious that noon happens for everyone at noon once clocks are synchronized. If 2 stones are dropped from a tower, they fall according to predictable timing. If planets orbit the sun, they do so in repeating periods. If a pendulum swings, it keeps rhythm. Nature appeared orderly and measurable. Newton gave that order mathematical form. His laws of motion and universal gravitation transformed scattered observations into a coherent machine-like cosmos. Suddenly, apples and moons belonged to the same framework. A falling object and a planet in orbit obeyed related principles. That was revolutionary. And because the equations worked so well, the assumptions behind them gained immense credibility. One of those assumptions was universal time. Let's see why it was so useful. Suppose you want to predict where a cannonball lands. You need its initial position, speed, direction, and the force of gravity. Then you calculate where it will be after 1 second, 2 seconds, 3 seconds. The same time variable applies everywhere in the problem. Now suppose you want to predict the orbit of Earth around the Sun. Again, position changes with time, velocity changes with time, acceleration changes with time. One shared clock governs the equations. This made physics elegant. Time was universal bookkeeping. You did not need separate personal times for planets or customized durations for stones. The universe ran on one schedule, and for the scales humans could measure then, this worked beautifully. That point matters. Newton's theory was not wrong in the casual sense. It was accurate across an enormous range of common situations. Even today, engineers often use Newtonian mechanics because it is simpler and more than adequate for bridges, buildings, baseballs, and most moving vehicles. If you throw keys onto a table, you do not need relativity. If you launch a deep space probe with exquisite precision, eventually you do. Science often advances this way. Older theories remain excellent approximations inside certain limits. So why did people come to think of the universe as mechanical? Because Newton's laws made prediction possible in a new way. Once you know forces and initial conditions, the future motion follows mathematically. The cosmos began to resemble a clockwork device. Gears, motions, causes, consequences, all operating according to precise laws. This image became famous during the Enlightenment. Nature was seen less as a realm of mystery and more as a system that could be understood rationally. The metaphor of the clock was irresistible. Clocks were among the most sophisticated machines of the age. They symbolized precision, regularity, and order. To compare the universe to a clock was to say it ran by dependable principles, and clocks themselves relied on repeating motion. Pendulums swung, gears turned, escapements clicked, hours accumulated. So it felt natural that the universe also possessed steady time in the background. There was a cultural harmony between technology and theory. The age of clocks imagined a clockwork cosmos. Now, there were philosophical critics even then. Gottfried Wilhelm Leibniz argued against Newton's absolute space and time. Leibniz preferred a relational view. To him, time was not an independent flowing thing, but a way of describing order among events. If nothing happened, what would it mean to say time passed? A fair question. Newton, however, treated time as real in itself. That debate foreshadowed later revolutions. But in practical science, Newton's approach won the era because it delivered results. Ships navigated better. Astronomy advanced. Engineering matured. Predictions matched observations. When a theory repeatedly succeeds, people understandably trust its worldview. So for generations, educated society inherited a specific mental picture. Space is a container. Time is universal. Matter moves inside both. Causes produce effects according to laws. The future is, in principle, calculable. This was intellectually powerful and psychologically comforting. Reality seemed intelligible. The heavens were no longer divine chaos, but orderly motion. There is something soothing about a lawful universe. Even today, many people instinctively think in Newtonian terms because daily life still resembles that world. You and a friend compare watches. A train leaves at a scheduled minute. A football match lasts a fixed time. Bread bakes for 20 minutes regardless of who checks the oven. Universal time appears obvious because the relativistic corrections are tiny at human speeds and common gravity. Nature hides its deeper complexity under normal conditions. Imagine two people walking in a park at different speeds. Relativity says their experienced times differ by an amount so small it is negligible. Newtonian time works perfectly well there. Likewise, clocks on a kitchen table and across town differ by so little that no one notices. So the old worldview survives not because it is ultimate, but because it is locally excellent. That is an important habit of mind in science. Useful is not the same as final. Approximate is not worthless. Newton's framework remains one of the greatest achievements in human thought. Yet beneath its success lay assumptions that later experiments would strain. One major issue concerned light. According to ordinary Newtonian reasoning, velocity should add straightforwardly. If a carriage moves forward and throws a ball ahead, the ball's speed relative to the ground combines with the carriage's speed. Simple enough. So if light behaves similarly, observers moving toward or away from a beam should measure different light speeds. But evidence began suggesting something stranger. The speed of light appeared constant. That was a crack in the old structure. Another issue involved electricity and magnetism. James Clerk Maxwell unified these forces in equations that implied light travelled at a fixed speed. How could that fit with Newton's absolute time and ordinary velocity addition? Scientists wrestled with this late into the 19th century. Some proposed invisible media like the luminiferous ether, a supposed substance filling space through which light waves moved. If such an ether existed, Earth's motion through it should be detectable. Experiments, especially the famous work of Albert A. Michelson and Edward W. Morley, failed to reveal the expected effect. The old assumptions were under pressure. Still, before relativity fully arrived, many people tried to preserve Newtonian time by patching other pieces instead. That tells us something profound about human thought. We do not surrender foundational intuitions easily. Universal time felt obvious, so alternatives were explored first. Then came Albert Einstein in 1905, who proposed keeping the laws of physics and the speed of light consistent for all inertial observers, even if that meant abandoning absolute time itself. This was a dramatic reversal. Instead of protecting universal time and modifying other concepts, Einstein kept physical laws elegant and let time become flexible. But before we leap ahead, it is worth pausing with Newton a little longer. His universe had grandeur. Planets traced predictable paths. Comets returned. Tides responded to gravity. Projectiles obeyed calculable arcs. Motion could be analysed rather than merely admired. This was not small progress. It was civilization-changing progress. It encouraged the belief that with enough data and intelligence, everything might be predictable. The French scholar Pierre-Simon Laplace later imagined an intellect that, knowing all forces and positions at one moment, could compute the entire future and past. This idea, often called Laplacian determinism, was the philosophical flowering of the mechanical universe. If the cosmos is clockwork and time universal, then reality is in principle fully calculable. Modern physics complicated that too with quantum uncertainty and relativity. But the dream itself was historically powerful. Now, from a modern perspective, Newton's absolute time can be seen the way we view a beautifully built map that omits mountains because it was designed for roads. Extremely useful. Elegant, not complete. There is no shame in that. All science advances through refinement. We do not mock old maps for lacking satellites. We appreciate what they made possible. Likewise, Newton's time remains embedded in everyday thinking because it still works so well nearby. When you set a timer for pasta, you are living happily in the Newtonian approximation. When satellites guide your route across a city, engineers quietly add Einstein in the background. That combination is rather charming. The kitchen trusts Newton. The navigation system consults relativity. As the night settles further, imagine the confidence of earlier centuries. A vast orderly universe, ticking with one shared rhythm, every motion governed by law, every event placed against a common time. It was a magnificent picture. By the end of the 19th century, physics looked confident. The motions of planets could be predicted. Machines obeyed known laws. Electricity and magnetism had been organised into elegant equations. Time still seemed dependable, universal, and evenly shared. Then one stubborn fact refused to cooperate. Light did not behave the way old intuition expected, and from that single inconvenience, one of the greatest intellectual shocks in history began. In 1905, Albert Einstein published a paper that would overturn centuries of assumptions. He was not an elderly academic surrounded by marble columns and obedient assistants. He was a young patent clerk in Bern, working through ideas in his spare time. There is something delightful about that. The universe was restructured partly by someone with office responsibilities. Einstein's first shock was simple to state and difficult to accept. Time depends on motion. Not feelings about motion, not opinions regarding motion. Actual measurable motion. Move differently through the universe, and time itself behaves differently. To appreciate why this was so startling, let us return briefly to the older picture. Under Newtonian thinking, time was absolute. If two people carried perfect clocks, then even if one rode a carriage and the other stood still, both clocks would keep the same time. Motion affected position, speed, momentum, perhaps hair arrangement in strong winds, but not time itself. Einstein challenged that. He began with two principles. First, the laws of physics should be the same for observers moving at constant velocity relative to one another. Second, the speed of light in vacuum is the same for all such observers. That second statement is where the trouble begins, because ordinary life trains us to expect speeds to add. If you walk forward inside a moving train and toss a ball ahead, someone standing outside sees the ball's speed as your throw, plus the train's speed. Reasonable. so one might expect light to behave similarly. If a spaceship moves toward a beam of light, perhaps it should measure the light approaching a little slower relative to itself, or if moving away, perhaps a little faster or slower depending on setup. Yet experiments and Maxwell's equations indicated otherwise. Everyone measures the same speed of light. This seems impossible if time and space remain rigid. So Einstein did something bold. He kept the speed of light fixed and allowed space and time to adjust. That sentence is easy to say now because history has softened it. At the time, it was radical. He was essentially telling humanity that the thing we trusted most, shared time, was less fundamental than the behaviour of light. Imagine revising your household around the cat's preferences instead of the walls. Strange, but effective if the cat is nature. Now let's build intuition carefully. Suppose you're inside a smooth spaceship moving steadily. You shine a flashlight upward to a mirror on the ceiling, and the light bounces back down. You measure how long this round trip takes. Inside the ship, the beam goes straight up and straight down. Simple. But to an observer watching the ship glide past from outside, the light does not travel vertically. While the beam moves upward, the ship moves sideways, so the beam traces a diagonal path up, then another diagonal path down. That path is longer. If both observers must agree on the speed of light, then something else must differ. The outside observer concludes the light took more time for the trip. That means the moving clock inside the ship appears to tick more slowly. This is time dilation. A moving clock runs slow relative to a stationary observer. Not broken slow, relativistically slow. The faster the relative motion, the stronger the effect. That is Einstein's first shock in working form. Motion changes elapsed time. A clock is any regular process, remember? A pendulum, atomic vibration, heartbeat, chemical reaction, aging body. If motion slows the clock, it slows all internal processes consistently. That means a traveller moving very fast ages more slowly relative to someone at rest compared with them. No special anti-aging cream required. Only inconvenient engineering. At everyday speeds, this effect is tiny. If you stroll to the kitchen, you do not return younger in any practical sense. If you drive to the shops, relativity does not cause awkward identification issues. Human speeds are far too small compared with the speed of light. But tiny does not mean zero. And once speeds become very high, the effect becomes substantial. This is where people often ask an important question. If motion is relative, can't each observer say the other is moving? Who then ages slower? Excellent question. The answer depends on whether observers remain in symmetric inertial motion, or whether one changes frames through acceleration and reunion. We will explore that more fully later with the twin paradox. For now, in simple comparisons between frames, each observer can indeed describe the other's moving clocks as slow according to their coordinates. Relativity is subtle, because simultaneity also changes, not just ticking rates. It is not a trick. It is a new geometry of space-time. That phrase deserves patience. Old intuition treats space and time as separate containers. Einstein showed they're intertwined. Distances and durations depend partly on the observer's state of motion. Two people can disagree about lengths, intervals, and simultaneity, while still agreeing on the deeper laws. Nature preserved consistency by sacrificing absolutes. This is elegant once the surprise settles. Now let's consider simultaneity, one of the most unsettling parts of special relativity. Imagine two lightning strikes hitting opposite ends of a long train. Someone standing midway on the platform sees the flashes arrive together and concludes the strikes happened simultaneously. A passenger moving with the train toward one flash and away from the other receives one flash earlier than the other. After accounting for the constant speed of light, that passenger concludes the strikes were not simultaneous. So motion changes not only clock rates, but also what counts as happening at the same time. That means there is no universal now shared by everyone. This was devastating to the old mechanical universe. Newton's absolute time had supplied a common present for all events. Einstein removed it. The universe became less like a factory whistle heard everywhere and more like a network of local perspectives linked by invariant laws. Still lawful, far stranger. You may wonder whether all this is merely philosophical wordplay. It is not. Special relativity produces measurable predictions repeatedly confirmed by experiment. Fast-moving unstable particles created in Earth's atmosphere survive longer than expected, because their internal decay clocks run slower relative to us. Muons, for example, reach the ground in quantities that classical timing alone would not explain. Particle accelerators routinely observe relativistic time dilation. Particles moving near light speed live longer in laboratory frames. Even precise clocks flown aboard aircraft have shown measurable differences compared with clocks left on Earth, though gravity also contributes depending on altitude. This is tested reality, not decorative theory. There is another consequence many people find surprising. As an object with mass moves faster and faster, it cannot simply keep gaining speed linearly until surpassing light. Reaching light speed would require impossible energy for massive objects. So the speed of light becomes a fundamental limit. Nature built a maximum signaling speed into space-time itself. That limit and time dilation are connected. The universe preserves light speed by adjusting measurements of space and time. Once more, consistency replaces intuition. Now pause for a quiet human thought. Before Einstein, time felt like the most stable thing imaginable. People doubted many matters, but not usually the sameness of seconds. Then physics discovered that seconds are not universal coins distributed equally to all motion states. A second for one path through space-time need not match another after comparison. This is humbling. It suggests our deepest assumptions are often local habits. Life on Earth at low speeds encouraged one picture. Wider reality turned out larger than that picture, and yet, relativity did not make the world chaotic. It made it more coherent. Instead of patching light into Newtonian time, Einstein found a framework where all inertial observers share the same laws. Truth became more subtle, not less trustworthy. That distinction matters in science. Sometimes complexity is not confusion. Sometimes complexity is accuracy. There is also comfort in knowing these strange effects do not intrude dramatically into ordinary evenings. Your tea cools on schedule, bread toasts approximately as expected. Conversations drift longer than intended for social reasons, not Lorentz factors. Everyday life remains mostly Newtonian because we move slowly relative to light. But above us, in accelerators, satellites, and cosmic rays, Einstein's corrections matter constantly. Even the title of our larger question, does time move faster in space, begins to sharpen here. If a spacecraft moves rapidly relative to Earth, motion alone tends to slow time aboard relative to Earth clocks. That is only half the story because gravity will complicate matters later. Sometimes space clocks run slower due to speed, sometimes faster due to weaker gravity. The final answer becomes a balance between effects. But Einstein's first shock gives us one pillar. Motion slows time, and not metaphorically, literally, measurably, operationally. As the evening grows calmer, imagine two identical clocks synchronize side by side. One stays home, one departs on a swift journey through the dark and later returns. They reunite no longer agreeing, no gears slipped, no batteries failed. The clock simply lived different motions. That possibility alone marked the end of the old universal schedule. Once Einstein's first shock had settled in, at least for those willing to let their worldview wobble a little, a practical question followed almost immediately. If motion changes time, then what happens to travellers? Not to abstract clocks in equations. not to idealize light pulses bouncing between mirrors, actual people, actual spacecraft, actual bodies growing older cell by cell? Would someone moving fast through space truly age more slowly than someone who stayed behind? According to special relativity, yes. And this is one of the most extraordinary results in all of physics, because it takes something deeply personal, aging, and places it inside mathematics. Wrinkles meet geometry. Birthdays meet spacetime. Your future dermatologist becomes indirectly relevant to Einstein. To understand why fast spacecraft age more slowly, we need to return to a central idea from special relativity. The speed of light in vacuum is constant for all inertial observers. That statement forces time and space to adjust when observers move relative to one another. Those adjustments include time dilation, meaning moving clocks run slower when viewed from another frame. Now remember what a clock really is in physics. Not merely a device with hands or digits. A clock is any repeatable process. A pendulum swinging, an atom vibrating, a heart beating, a chemical reaction progressing, DNA repairing, cells dividing, thoughts occurring in sequence. Aging is built from countless physical processes. So if motion slows the rate at which time accumulates along a traveller's path relative to another observer, then aging slows as well. This does not mean the traveller feels slowed. That misconception is common. Inside the spacecraft, everything feels normal. Your pulse feels normal. Your thoughts feel normal. Your coffee becomes disappointingly cold at an ordinary pace. Your onboard clock ticks 1 second per second, as clocks stubbornly tend to do locally. The difference appears only when comparing with someone who followed a different path through space-time. That point cannot be overstated. Relativity is not about feeling strange during travel. It is about comparing elapsed time after different journeys. Let's picture two twins, since twins have also contributed generously to physics discussions over the years. One twin remains on Earth. The other boards a spacecraft capable of travelling at a very high speed, perhaps close to the speed of light, turns around later and returns. When they reunite, the travelling twin has aged less. Not symbolically, not emotionally, physically. Fewer years have passed for them. This is often called the twin paradox, though it is not a paradox once the geometry is understood. We will treat it more fully later, but it serves here as a useful preview. Why does this happen? Because in relativity, elapsed time depends on the path taken through space-time. Different routes between reunion events can contain different amounts of proper time. Proper time is the time measured by a clock carried along the path itself. Your wristwatch measures your proper time, so does your body. If two people separate and reunite after following different motions, their proper times can differ. That is the core fact. Now let us make it intuitive without drowning in equations. Suppose a spacecraft travels at 90% of the speed of light relative to Earth. That is unimaginably fast by ordinary standards, around 270,000 kilometers per second. Fast enough to make motorway traffic seem deeply reflective and still. At that speed, time dilation becomes large. A clock aboard the ship ticks slower relative to Earth clocks by a noticeable factor. If 10 years pass on Earth, fewer years might pass on board, depending on the exact speed and travel profile. Increase the speed further, say 99% of light speed, and the effect grows stronger. At 99.9%, stronger still. As velocity approaches light speed, the disparity can become dramatic. This leads to one of the most famous possibilities in physics: travel to the future. Not by magic portals, not by brass machines with excessive levers, by fast motion. If astronauts travelled to a distant star system at relativistic speed and returned, they might experience a handful of years while decades or centuries passed on Earth. They would step into Earth's future. This is allowed by known physics. The engineering remains another matter entirely. To accelerate a large spacecraft anywhere near light speed requires immense energy, shielding, life support, navigation precision, and solutions to several unpleasant problems involving dust particles becoming dangerous at high velocity. Still, the principle stands. Relativity permits one-way travel into the future through high-speed journeys. Now, an important subtlety. People often ask, why doesn't Earth see itself as moving while the spacecraft is at rest? Relativity does say uniform motion is relative, but in reunion scenarios symmetry breaks because the spacecraft must accelerate, turn around, and decelerate. The Earthbound twin remains approximately in one inertial frame for much of the story, while the traveller changes frames. That change matters. The universe keeps careful records of paths. Spacetime geometry notices who turned around. This is why the travelling twin returns younger. Not because acceleration directly causes aging loss in a simplistic sense, but because the total proper time along the traveller's path is shorter. It is a route difference. Imagine two hikers leaving the same cabin and meeting later at another. One takes a long winding route, another a shorter path. They both walked honestly, but their step totals differ. Relativity offers something analogous with time. Different journeys accumulate different durations. Now, special relativity concerns motion without gravity, or with gravity neglected. Later, general relativity adds gravity into the picture and complicates everything delightfully. But even within special relativity alone, the consequences are enormous. First, simultaneity becomes relative. Second, lengths contract in the direction of motion as seen by outside observers. Third, moving clocks run slow. These effects are not separate tricks. They are connected features of one structure. Space and time form spacetime. Form. When motion changes one observer's measurements, the system adjusts consistently. There is no cheating, no hidden contradiction. Just geometry more sophisticated than common sense evolved to expect. Let us consider what astronauts would notice personally. Imagine you're aboard a high-speed mission. You wake, eat, exercise, work, sleep. Days feel ordinary. You celebrate birthdays according to onboard calendars. Your metabolism proceeds normally from your perspective. If you call Earth, signal delays may become substantial due to distance, but your own inner tempo feels unchanged. Yet when comparing clocks later, you discover Earth advanced more than you did. That is the strange elegance of relativity. Your life feels normal while history elsewhere accelerates relative to your journey. There is something emotionally powerful in that idea. A traveller could leave a familiar world and return to a future they never personally lived through. Friends older, cities changed, languages shifted. Cultures transformed, all because velocity altered elapsed time. Science fiction loves this concept because physics introduced it first, and unlike many fictional devices, this one rests on experimentally verified principles. Now let's be honest about scales. Could commercial airline passengers use this to avoid birthdays significantly? No. Aircraft speeds produce tiny effects. Measurable with precise clocks? Yes. Socially useful? No. Could race car drivers exploit it? Still no. Could a person jogging enthusiastically around the park become meaningfully younger than their sofa-bound neighbour? Also no, though the health benefits remain excellent for unrelated reasons. Relativistic aging differences become significant only at speeds approaching light speed or over long durations with high precision. Human intuition often fails here because we think in kilometers per hour, not fractions of c, the speed of light. The light barrier is vast. Nature gave us plenty of room for ordinary life before relativity becomes dramatic. Still, tiny effects are real effects. Muon particles produced high in Earth's atmosphere survive longer in our frame because they move so quickly. Without time dilation, many would decay before reaching the ground. Particle accelerators routinely observe longer particle lifetimes at high speeds. These are not philosophical anecdotes, they are laboratory realities. Now, another subtle point worth appreciating before sleep claims victory. When we say, the spacecraft ages more slowly, we always mean relative to some comparison frame and eventual reunion or communication scheme. Relativity is relational. There's no absolute cosmic judge announcing who truly moved in all contexts. Yet when paths diverge and rejoin, proper times become directly comparable. That is where predictions become concrete. Two clocks meet again. Readings differ. Case closed. This practical clarity is why relativity moved from strange theory to accepted science. Nature sided with Einstein repeatedly. There is also a beautiful consequence for interstellar dreams. Distances that seem enormous from Earth can become more manageable for travellers because of length contraction in the traveller's frame combined with time dilation effects. A journey to a star several light years away may involve many Earth years externally, yet fewer personal years on board if speeds are sufficiently high. The stars remain distant, but relativity changes how journeys are experienced. Again, engineering is merciless, but physics allows imagination some room. Now picture humanity centuries from now, perhaps with propulsion systems beyond today's reach, ships departing for long missions, crews aging modestly while civilizations back home race ahead through decades. Explorers not merely crossing space, but crossing unequal time, every return a reunion and an historical shock. That possibility follows naturally from special relativity. No wormholes required, just speed. As the evening quiets further, notice how this changes our original question. Does time move faster in space? If you're in a fast-moving spacecraft, motion alone makes your onboard time pass more slowly relative to Earth. So in one sense, no. Time does not simply move faster in space. Fast travel can slow your elapsed time. But space missions also occur farther from Earth's gravity, which can speed clocks relative to ground clocks. That means competing effects exist. Velocity slows time. Weaker gravity speeds time. Which effect wins depends on circumstances. For low Earth orbit astronauts, both effects matter. For deep space travellers at great speed, motion can dominate. We are building the full answer piece by piece, and perhaps that is the best way to approach relativity. Slowly, calmly, one surprise at a time. So we now know why fast spacecraft age more slowly. Their path through space-time contains less proper time than the path of those who remain behind. Not because bodies become lazy, not because clocks become sentimental, because motion reshapes duration itself. And once theory says this so confidently, the next question becomes irresistible. Has anyone actually measured it with real clocks? A theory can be elegant. It can be mathematically beautiful. It can explain puzzles that troubled earlier science. It can inspire generations of students to stare thoughtfully at ceilings. And yet none of that is enough. Physics, in the end, must survive contact with measurement. So after Einstein proposed that motion changes time, the obvious next step was simple to state and difficult to accomplish. Can we test it? Can we place clocks on different journeys, reunite them, and see whether time itself has kept different accounts? The answer is yes. And to do it properly, humanity needed clocks far better than pendulums, better than spring watches, better than wall clocks that gain 2 minutes and pretend innocence. We needed atomic clocks. These are among the most precise instruments ever built. They do not keep time by gears turning or weights falling. They rely on the natural frequency of atoms, especially the incredibly stable transitions between energy states in atoms, such as cesium or rubidium. In simple terms, atoms behave like microscopic metronomes with astonishing consistency. Count enough of their oscillations, and you have a second. That means atomic clocks can detect differences so tiny they would embarrass ordinary clocks into silence. And those tiny differences are exactly what relativity predicts for common human speeds and heights. So atomic clocks became the perfect judges. If time dilation was real, they would notice. If Einstein was wrong, they would expose him. There is something satisfying about that arrangement. No speeches, no popularity contest, just clocks. Let's start with one of the most famous tests. In 1971, physicists Joseph Hafele and Richard Keating took portable atomic clocks aboard commercial airliners and flew them around the world, eastward and westward, comparing them with clocks that remained on the ground. This was not the glamorous science fiction image of relativity. No sleek silver starship, no glowing engines, just air travel, luggage, schedules, and extremely expensive clocks. Yet it was enough. According to Relativity, clocks on aircraft should experience two main effects. First, because the planes were moving relative to Earth's surface, special relativity predicted their clocks would tick more slowly. Second, because the planes flew at altitude, farther from Earth's centre, and in weaker gravity than clocks on the ground, general relativity predicted their clocks would tick faster. These effects compete. Motion slows time, weaker gravity speeds time. The exact result depends on speed, altitude, direction, and Earth's rotation. That last detail matters because eastward flights move differently relative to Earth's rotational frame than westward flights. After the flights, the clocks were compared. The measured differences matched relativistic predictions within experimental uncertainty. Not perfectly, because real experiments involve noise, corrections, and the eternal human tradition of messy logistics. But clearly enough, time dilation had left fingerprints on airline tickets. Imagine telling Newton that future scientists would test the flexibility of time using passenger aircraft. He might have asked about baggage fees first. Now some critics at the time debated precision details of the experiment, as scientists should. That is healthy skepticism, but later experiments with better clocks and cleaner methods repeatedly confirmed the same principles. Relativity did not depend on one airplane adventure. It kept winning. There are many ways to test time dilation. Another powerful source comes from particle physics. Certain unstable particles decay after predictable lifetimes. They act as natural clocks because their probability of decay follows measurable timing laws. One famous example is the muon. Muons are created when cosmic rays strike Earth's upper atmosphere. At rest, muons live only a tiny fraction of a second before decaying. Given their short lifetime, many should vanish before reaching the ground, and yet many do reach detectors at Earth's surface. Why? Because they are moving extremely fast relative to us. Their internal clocks run slower in our frame. Time dilation extends their observed lifetime enough for them to travel much farther than classical expectations suggest. This is not a philosophical argument. It is counted in detectors. The sky rains evidence for relativity. There is also a complementary viewpoint from the muon's frame, where atmospheric thickness is length contracted. Relativity remains consistent whichever frame you analyse properly. That symmetry is one reason the theory is so robust. Now let's return to atomic clocks, because they only became more impressive with time, which is fitting. As technology improved, scientists could detect relativistic differences from smaller and smaller changes in motion and height. Clocks on mountains run differently from clocks near sea level. Clocks raised by only modest vertical distances can show measurable gravitational time shifts with sufficiently advanced equipment. In some modern experiments, clocks separated by less than a meter in height can detect different ticking rates due to gravity. That sentence should be enjoyed slowly. Move a clock upward by a small height, and time changes measurably. The universe is doing relativity in staircases. Most people never notice because the differences are tiny, but tiny is not imaginary. Tiny simply means your kitchen timer lacks ambition. Modern optical atomic clocks are so precise that if they ran for immense spans of time, they would drift by astonishingly little. They are precise enough to sense changes in gravitational potential, and may one day be used as tools for geodesy, measuring Earth's shape and gravitational field through time differences. In other words, clocks are becoming terrain sensors. Mountains can influence timekeeping. Physics occasionally sounds invented, yet remains rude enough to be true. Now consider satellites. The global positioning system depends on satellites carrying atomic clocks. These satellites orbit Earth rapidly and at high altitude. Special relativity says their motion slows onboard clocks. General relativity says weaker gravity at orbital altitude speeds them up. The net effect is that satellite clocks tick differently from clocks on Earth, by amounts large enough to ruin navigation if ignored. So engineers pre-correct and continuously manage timing. Without relativity, GPS positions would drift dramatically. That means every time someone uses map navigation to find a cafe, a hospital, or the wrong exit, relativity is involved. Not always successfully, but involved. This is one of the strongest cultural moments in modern science. A theory once dismissed as bizarre became routine infrastructure. Your phone quietly trusts Einstein many times a day. Now, let us talk about what atomic clocks actually compare. They do not detect mystical flowing substances, they compare counted cycles. If one clock records fewer cycles than another after separate journeys, then less proper time has elapsed along that clock's path. That operational clarity is why time dilation is so solid scientifically. We do not need metaphors, we have numbers. Two clocks meet. They disagree. Repeat under controlled conditions. Predict with equations. Match observed results. Science smiles quietly. There is also a beautiful humility in this story. Human senses cannot detect these tiny relativistic effects directly in daily life. You do not feel 1 nanosecond. You do not notice a slightly different aging rate after climbing a hill. So if we relied only on intuition, we would conclude time is rigid. Instruments extended perception beyond instinct. This happens often in science. Telescopes revealed moons and galaxies. Microscopes revealed cells and microbes. Atomic clocks reveal that even ordinary environments do not share perfectly uniform time. Precision tools keep discovering that reality is subtler than it first appears. Now imagine two identical clocks synchronized in a laboratory. One remains on a table, the other is flown on a route around the world and returned. When compared, they differ slightly. That small disagreement contains an enormous philosophical message. Time is not universal bookkeeping, it is path-dependent. Motion and gravity matter. The world is not built from one giant invisible wall clock over everyone's heads. Instead, every clock participates locally in space-time. That insight moves us closer to our title question again. Does time move faster in space? Atomic clocks say the answer depends. Raise a clock higher above Earth, and gravity tends to make it run faster. Move that clock rapidly in orbit and motion tends to slow it. Balance both, and you get the real result. No guessing required. Measure it. And we have. Repeatedly. Now, perhaps the most charming aspect of atomic clocks is how calm they are about all this. They do not dramatize. They do not write essays. They do not argue online. They simply tick according to physics and reveal what the universe is doing. There is wisdom in that. If more disputes were settled by portable cesium standards, life might be quieter. Picture an atomic clock in a laboratory vault, another in an aircraft cabin, another aboard a satellite, another perhaps one day on the Moon or Mars, each counting steady internal rhythms, each tracing a different path, each gathering its own share of elapsed time. And when brought into comparison, they tell the same story Einstein began. Motion alters time. Gravity alters time. Clocks remember where they have been. That last phrase is almost poetic, but also technically useful. A clock's reading is history written in numbers. And once we accept that, a famous question waits just ahead. If travellers can return younger than those who stayed behind, is the twin paradox really a paradox at all? Few ideas in relativity have caused more fascination, more confusion, and more determined napkin diagrams than the twin paradox. It sounds simple enough. Two identical twins begin together at the same age. One stays on Earth, The other boards a fast spacecraft, travels far away at very high speed, turns around, and returns. When they meet again, the travelling twin is younger. Less time has passed for the traveller. This result follows directly from relativity. And yet many people immediately object. Wait a moment. Motion is relative, isn't it? Couldn't the traveller say Earth was moving instead? Shouldn't each twin think the other ages more slowly? How can one come back younger without contradiction? That tension is why it gained the dramatic label paradox. But the good news is this: there is no contradiction. There is only geometry, symmetry, and one important difference between the twins' experiences. Tonight we will explain it gently, without requiring panic, chalk dust, or aggressive algebra. Let's begin with what is true. During steady relative motion, each observer can describe the other's moving clocks as running slow, according to their frame. That is a genuine feature of special relativity. If two spacecraft glide past each other smoothly at constant speed, each may judge the other's clocks as ticking slower once simultaneity is handled correctly. This symmetry often confuses people when they first hear about the twin story. If each sees the other slow, how can one twin end younger? Because the twins do not remain in symmetric situations. One stays in roughly the same inertial frame on Earth. The other departs, turns around, and returns. That traveller changes frames, and that breaks the symmetry. This is the heart of the whole matter. Not twins, not youthfulness, not family competition. Frame changes. Imagine two people taking different routes through a city and meeting later at the same cafe. One walks directly there, the other takes a scenic route, circles a fountain, boards a tram briefly, changes direction twice, and eventually arrives. They started together, they reunite together. Yet they need not have walked the same distance. Different paths can produce different totals. Relativity says something similar about time. Different paths through space-time can produce different amounts of proper time. Proper time is the time measured along a traveller's own path by a clock they carry. Your wristwatch measures your proper time. Your body does too. So in the twin scenario, the twins follow different world lines, meaning different histories through space-time between departure and reunion. The Earth twin follows one path. The travelling twin follows another. Those paths contain different elapsed proper times. The traveller's path can contain less. That is why the traveller returns younger. Now let us slow down and picture the journey. Twin A remains on Earth. Twin B departs in a spacecraft at very high speed. During the outbound leg, Twin B sees Earth receding. At some distant point, Twin B turns around. Then Twin B returns at high speed. Eventually they meet again. When clocks are compared, Twin B has experienced less time. No mystery remains once reunion occurs. Clocks can be placed side by side. Readings differ. Nature has spoken. The only real question is how to understand it. One common misunderstanding is to think acceleration itself is the entire cause. The turnaround involves acceleration, yes, and it matters because it changes frames. But saying acceleration caused all the aging difference is incomplete. The deeper statement is that the total proper time along the traveller's path is shorter than along the stay-at-home path. Acceleration helps create that non-symmetric path. It is part of the story, not the whole philosophical point. Think of bending a route versus walking straight. The turning matters because it changes the route, but the final distance depends on the entire path. Now, some listeners may reasonably ask, couldn't Earth also be considered moving in some sense? Relativity does not provide one universal state of rest. Motion is relative in inertial frames. However, the Earth twin in the standard simplified scenario remains approximately in one frame throughout, while the traveller switches from outbound inertial motion to inbound inertial motion. That switch changes which distant Earth events count as simultaneous from the traveller's perspective, and this is where simultaneity becomes important again. In relativity, observers moving differently do not agree on one shared distant now. During the outbound leg, the traveller assigns one set of simultaneous Earth moments. After turnaround during the inbound leg, the traveller assigns another set. When changing frames, the traveller's notion of which Earth time is now shifts. That shift helps explain how Earth can accumulate more time consistently. This sounds technical, but it is not magic. It is bookkeeping in a universe without universal simultaneity. If that still feels slippery, do not worry. Many intelligent people dislike simultaneity on first meeting. It improves with familiarity. There is also a wonderfully clean mathematical picture using spacetime diagrams. In Euclidean geometry, the straight line between 2 points is shortest. In Minkowski spacetime, the geometry relevant to relativity, inertial straight world lines between two reunion events maximize proper time, compared with certain detouring accelerated paths. That means the twin who remains inertial longer can experience more elapsed time than the twin who departs and returns. This sounds upside down only because space-time geometry differs from everyday geometry. Nature enjoys variety. Now let's use numbers lightly. Suppose the spacecraft travels at a speed where time dilation is strong enough that for every 10 years passing on Earth during cruise phases, only 6 years pass for the traveller. If the mission includes outbound and inbound legs arranged symmetrically, Earth might age 20 years while the traveller ages 12, plus some smaller details depending on acceleration phases. When they reunite, the traveller is 8 years younger than the sibling, not emotionally younger, biologically younger, fewer heartbeats, fewer cell divisions, fewer birthdays celebrated, though possibly more stories told. This result has never required twins specifically. Twins simply dramatize comparison because they begin with matching ages. Any two synchronized clocks would do. Indeed, physics prefers clocks because they complain less. Take one atomic clock on Earth, send another on a high-speed journey and bring it back. Compare, differences appear. The universe is perfectly happy to demonstrate the twin paradox with machinery. Now, is this science fiction only? No. We do not yet send humans on near-light speed round trips, but the principle has been tested in smaller forms. Fast-moving particles live longer than stationary expectations predict. Atomic clocks flown on aircraft differ from clocks left on Earth. Satellites require relativistic timing corrections. All of these are cousins of the twin story. The dramatic interstellar twin version is simply the same physics at larger scale. There is also a human side to why this thought experiment captures imagination. It turns time into something personal. Many relativistic effects involve equations, beams of light, reference frames, or abstract measurements. But twins aging differently strikes closer to home. It says time is not just what clocks do in laboratories. It reaches into lives, families, generations, memory. One sibling could leave and return to a future the other lived through. That idea is emotionally powerful. It also reminds us that aging is a physical process, and physical processes obey space-time structure. Even our most intimate timelines are subject to geometry. Now let's address another frequent worry. What if the traveller accelerates only briefly? Can a short turnaround really matter so much? Yes, because it is not the duration of acceleration alone that determines the outcome. Even a brief turnaround can connect two long inertial legs and create a path with less proper time overall. Again, root geometry matters more than dramatic engine noise. Another concern. Would the traveller feel younger during the trip? No one feels younger relative to themselves. You always experience your own proper time normally. Hunger arrives on schedule. Sleepiness visits. Socks go missing in luggage according to timeless principles. The difference is comparative after reunion. Relativity does not grant subjective immortality. It grants unequal elapsed durations between paths. Now imagine future deep space exploration. A crew departs for a relativistic mission, lasting, by their onboard clocks, 5 years. They return to Earth and discover 20 years passed here. their friends older, children grown, technology transformed, cities redesigned. They personally lived 5 years. Earth lived 20. This is one-way travel into the future, and it emerges naturally from the same reasoning as the twin paradox. No wormholes required, only speed and return. Now, a subtle but important reminder for our larger topic. The twin paradox usually emphasizes motion-based time dilation from special relativity. But in real missions, gravity also matters. Near massive bodies, clocks run differently too, so space travel timing often combines velocity effects and gravitational effects. A fast ship far from gravity may age differently than one orbiting a planet. The universe rarely settles for one variable when it can offer several. Still, the twin scenario remains the clearest doorway into personal relativity. Two beings start together, two beings reunite. Different times have passed. That statement alone would have stunned earlier centuries. Newton's universe allowed one shared time for both. Einstein's universe allows different elapsed times without contradiction. That is progress through deeper honesty. As evening grows quieter, perhaps picture the twins not as rivals but as witnesses. One witnesses the continuity of home, the other witnesses the flexibility of time. Both are correct from where they lived. Both carry truthful clocks, and when they embrace again, their watches tell a story no philosophy could invent before measurement made it real. So the twin paradox is not a paradox after all. It is a lesson that symmetry can be broken by different journeys, and that time belongs not to everyone equally, but to each path individually. Just when the universe seemed strange enough, Einstein added a second surprise. Motion changes time, yes. Fast travel can slow aging relative to those left behind, yes. Clocks on different journeys can disagree, yes. That would already be a lifetime achievement for most scientific revolutions. But Einstein was not finished. A decade after special relativity, he introduced an even deeper theory, general relativity. And with it came the second shock. Gravity changes time too. Not only rockets, not only speed, not only dramatic near-light adventures, gravity itself alters how quickly clocks tick. This idea remains one of the most elegant and unsettling truths in physics, because gravity is familiar. We drop things in it, walk through it, complain about stairs because of it. It feels ordinary. Yet hidden inside ordinary gravity is a distortion of time. The stronger the gravity, the slower time passes relative to regions of weaker gravity. That sentence is worth meeting slowly. A clock lower in a gravitational field runs more slowly than a clock higher up. A clock near a massive object runs more slowly than one farther away. You right now are living in time slightly slowed by Earth's gravity compared with someone much farther from Earth. The difference is tiny. The principle is enormous. To understand how Einstein arrived here, we need one of his most famous insights, the equivalence principle. Imagine you're inside a sealed elevator, no windows, no clues. If the elevator is standing still on Earth, you feel pressed gently to the floor. Now imagine the same elevator floating far from planets in empty space, but accelerating upward with engines. You would feel pressed to the floor in much the same way. Locally, those situations are equivalent. Gravity and acceleration can mimic one another. Einstein took this simple observation with extreme seriousness. Where others saw an interesting curiosity, he saw a doorway. If acceleration and gravity are deeply linked, then effects found in accelerating systems should tell us something about gravity. Now picture a beam of light crossing that accelerating elevator from one wall to the other. While the light travels, the elevator moves upward. So to someone inside, the beam appears to curve downward slightly. From this, Einstein reasoned that gravity should also bend light. Later observations confirmed that massive bodies can indeed bend light paths, but another consequence follows. Suppose light travels upward inside that accelerating elevator from floor to ceiling. By the time it arrives, the ceiling is moving relative to where the light was emitted. The received light changes frequency. Translated into gravity, light climbing upward out of a gravitational field should lose energy and shift in frequency. This is gravitational redshift, and hidden inside that effect is the changing rate of time. Because frequency is cycles per unit time, if frequencies differ with height, clock rates differ with height, so gravity and time are entangled. Now let's strip away the formalism and use intuition. Think of gravity not merely as a force pulling objects downward, as in Newton's picture, but as curvature in space-time caused by mass and energy. Mass tells space-time how to curve. Curved space-time tells matter how to move. That famous summary captures the spirit of general relativity, and since time is part of space-time, curvature affects time itself. Near massive objects, the time dimension behaves differently. Clocks deeper in the gravitational well tick more slowly relative to clocks higher up. This is gravitational time dilation. The term sounds technical, but the meaning is direct. Gravity changes elapsed time. Imagine two identical clocks. One sits on the ground floor of a building. One sits on the roof. Leave them long enough with sufficient precision, and they will not agree perfectly. The lower clock, closer to Earth's centre, runs slightly slower. This has been measured. Reality does relativity in office towers. Now scale that upward. A clock on Earth's surface runs slower than a clock far away in deep space, all else equal. A clock near the moon runs differently than one near Earth. A clock near a neutron star runs far more differently. A clock near a black hole enters territory where common sense packs its bags and leaves quietly. Before we reach such extremes, let us appreciate the everyday subtlety. You do not feel your time slowed. No one wakes and says, "Gravity seems temporarily aggressive today." Locally, your body and clocks proceed normally. Your heartbeat feels normal. Your tea cools normally. Your emails arrive at regrettably normal speed. Differences emerge only when comparing clocks at different gravitational potentials. This parallels motion-based relativity. You always experience your own local time as ordinary. The strangeness appears in comparison. That is one of the recurring lessons of modern physics. Reality is relational. Now, some people ask whether stronger gravity means everything simply slows equally, making the effect meaningless. But comparisons make it meaningful. If all clocks in one region run slower relative to another region, and signals exchanged between those regions reveal it, then the difference is physical. It affects navigation, communication, and measurable outcomes. Noticing requires comparison. Existence does not. There is also an important distinction between feeling weight and experiencing gravitational time dilation. Standing on Earth's surface, you feel weight because the ground prevents your natural freefall path. Astronauts in orbit feel weightless, not because gravity vanished, but because they are continuously falling around Earth. Meanwhile, clock rates depend on gravitational potential and motion, not merely the sensation of heaviness. So weight and time are related only indirectly. Physics enjoys separating ideas humans tend to blend together. Now let's talk history. Einstein published General Relativity in 1915. It was mathematically demanding and conceptually bold. It predicted phenomena beyond Newton's gravity, including the precession of Mercury's orbit and bending of starlight near the Sun. During the 1919 solar eclipse, observations led by Arthur Eddington helped publicize the theory worldwide by supporting light-bending predictions. Einstein became internationally famous, but gravitational time dilation took longer to verify directly with precision experiments, because measuring tiny timing differences requires excellent clocks. Once atomic clocks arrived, gravity's influence on time moved from theory into routine measurement. That matters because it transformed a philosophical-sounding claim into engineering fact. Gravity is not merely pulling apples, It is shaping clocks. There is something almost mischievous in that. The same phenomenon blamed for dropped toast also edits timekeeping. Now consider our broader question. Does time move faster in space? Einstein's second shock points strongly toward yes, in one sense. Farther from Earth, gravity is weaker. Weaker gravity means clocks tend to run faster than clocks on Earth's surface. So a clock in orbit or deep space may gain time relative to one on the ground due to gravity. But remember the first shock. If that clock is also moving quickly, motion slows it. So space clocks experience a contest. Velocity tries to slow them. Weaker gravity tries to speed them. The final answer depends on which effect wins. That is why orbiting satellites require careful calculations rather than slogans. Now let's imagine an extreme example. Suppose one person lives near a very massive object, perhaps close to a black hole, but still safely outside disaster range. Another person remains far away. The one near the black hole experiences their local hours normally. They eat meals, speak, think, rest. Yet far away, much more time may pass. Return later and entire eras could have unfolded elsewhere. This dramatic version has entered popular culture through films and novels, but it is rooted in real relativity. Gravity can separate timelines. Again, not by magic, by geometry. There is also a philosophical consequence. Newton treated time as universal background and gravity as force acting within it. Einstein made gravity a feature of space-time itself. That means gravity no longer happens inside time unchanged. Gravity participates in shaping time. The stage and the actors are no longer separate. The stage bends. And because time bends with it, the old mechanical universe becomes something richer and less intuitive. Many people find this disturbing at first, yet there is comfort in it too. The universe is not rigidly indifferent, it is responsive. Mass changes structure, motion changes measurement, context matters. Two clocks can disagree honestly because reality gives each a different environment. That is subtler than the old worldview, but perhaps more generous. As evening deepens, imagine clocks scattered through the solar system. One on Earth, one on the Moon, one aboard a satellite, one drifting between planets, one near Jupiter, each ticking locally, faithfully and differently according to motion and gravity. No master clock correcting them from above, only laws relating their readings. This is Einstein's second shock. Gravity does not merely pull objects downward, it reshapes duration. If gravity changes time, then we need to understand the stage on which this happens. What exactly is space-time, and how can something invisible curve at all? If Newton gave us a universe built like a machine, Einstein replaced that machine with geometry. That may sound like an unusual renovation plan, but it changed physics forever. In Newton's world, gravity was a force acting across space. The Earth pulled the Moon, the Sun pulled Earth. Apples fell because Earth exerted gravitational attraction. Space was the stage, time was the schedule. Matter moved inside both, it worked brilliantly. Yet one awkward question remained. How does one object reach across empty space and pull another instantly? Newton himself was uneasy about action at a distance. His equations predicted motion beautifully, but the mechanism behind gravity remained mysterious. Einstein approached the problem differently. Instead of asking how masses pull one another through space, he asked whether gravity might not be a force in the old sense at all. What if falling objects are simply following the natural shape of reality? That thought led to general relativity, and with it came one of the most powerful ideas ever proposed. Mass and energy curve space-time, and objects move through that curved space-time along the straightest paths available. Now we should slow down and unpack that carefully. First, what is space-time? We usually speak of space and time separately. Space is where things are, time is when things happen. 3 dimensions of space, left, right, forward, backward, up, down, 1 dimension of time, earlier, later. Einstein's insight was that these are not independent boxes stacked beside each other. They form one interconnected structure, space-time. Events are located not just by position, but by position and time together. You're not merely in a room, you're in that room at this moment. Every event has an address in space-time. That alone is already a conceptual shift. But then comes curvature. When people first hear curved space-time, they often imagine something folded into a higher invisible room, like a blanket draped over furniture. That image can help loosely, but it also misleads if taken too literally. Curvature in geometry means the rules of distance and straightness differ from flat space. For example, on the surface of Earth, 2 people starting at the equator and walking north along different longitudes eventually meet at the North Pole. On a flat map, parallel lines would not meet. On a curved surface, geometry changes. General relativity says something analogous happens in 4-dimensional space-time. Near mass and energy, the geometry is not flat. Distances, paths, and time intervals behave differently. Objects then move according to that geometry. This is why planets orbit stars without requiring invisible pulling ropes. Earth follows a natural path through the curved space-time around the Sun. The Moon follows a natural path around Earth. An apple released from a tree follows a path through Earth's local curved space-time. The apple is not being yanked downward in the old intuitive sense. It is moving along the geometry available to it. The ground then interrupts that path rather abruptly. This is why standing still on Earth is, in a sense, less natural than freefall. Astronauts in orbit feel weightless because they are freely following curved space-time around Earth. They are falling continuously while missing the ground. That phrase never gets old. Orbit is falling with excellent aim. Now let us revisit Einstein's equivalence principle, because it was the seed of all this. If you're inside a sealed elevator in deep space accelerating upward, objects dropped from your hand fall to the floor. If you're inside a stationary elevator on Earth, objects also fall to the floor. Locally, those situations can be indistinguishable. This suggested gravity and acceleration are deeply related. Einstein followed that clue far beyond where anyone expected. If acceleration can mimic gravity, perhaps gravity is not a mysterious force at all, but a consequence of moving in curved space-time. That was the leap. And it required mathematics sophisticated enough to describe curved geometries generally, much of it connected to work by Bernhard Riemann and later developed into the tensor language Einstein needed. General relativity is famous partly because the ideas are elegant and the equations are demanding. The field equations relate the distribution of mass energy to the curvature of space-time. In broad spirit, matter tells space-time how to curve. Curved space-time tells matter how to move. That summary is not the equations, but it captures the heart of them. Now, what does curved time specifically mean? We touched on gravitational time dilation earlier. In stronger gravity, clocks run more slowly relative to clocks farther away. This happens because time is part of the geometry being curved. Near a massive body, the temporal dimension is affected, not just spatial paths. So if 2 identical clocks are placed at different altitudes, the lower one ticks more slowly. The difference may be tiny near Earth, dramatic near dense objects, and extreme near black holes. This is not metaphorical slowing. Real clocks measure it. Atomic clocks confirm it. GPS systems must account for it. Your phone's navigation quietly depends on curved space-time every day. There is something pleasing about that. People use relativity to locate sandwich shops. Now let's talk about straight lines, because relativity uses the word differently. In flat everyday space, a straight line seems obvious. Stretch a string. Use a ruler. There it is. In curved geometry, the equivalent idea is called a geodesic, the straightest possible path allowed by the space. On Earth's surface, long airplane routes often look curved on flat maps, because they follow great circle paths, which are geodesics on a sphere. Likewise, planets follow geodesic-like paths in curved spacetime. They are not choosing circles because they enjoy symmetry, they are responding to geometry. This means gravity is less like a tug and more like guidance by structure. That is a subtle but profound change in worldview. Newton said gravity acts. Einstein said geometry governs. Now, did general relativity actually work? Yes, repeatedly. One early triumph involved the orbit of Mercury. Mercury's perihelion, the point of closest approach to the Sun, shifts over time. Most of this could be explained by known planetary influences, but a small leftover discrepancy remained under Newtonian gravity. General relativity predicted exactly the missing amount. That was a major success. Another famous prediction was the bending of light by gravity. If space-time is curved, light should follow curved paths near massive bodies. During the 1919 solar eclipse, expeditions led by Arthur Eddington measured apparent star positions near the Sun and found deflections consistent with Einstein's prediction. The results made Einstein world famous. More modern observations have confirmed such effects with far greater precision. Today we see gravitational lensing across the cosmos, where galaxies and clusters bend light from more distant objects, creating arcs, magnified images, and multiple apparent sources. The universe sometimes behaves like an enormous glass lens made of gravity. Then there are gravitational waves. General relativity predicted that accelerating masses could create ripples in space-time itself. A century later, the LIGO scientific collaboration detected waves from merging black holes. Space and time literally rang like a struck bell. Not audibly, of course, but measurably. Einstein's geometry continued to pass tests long after his death. Now, because this is science for sleep, let us be honest about one challenge. Curved space-time is not easy to visualize. We evolved to throw objects, avoid holes, and find snacks. We did not evolve to intuit four-dimensional pseudo-Riemannian manifolds. So confusion is not failure, it is expected. The best approach is to keep the operational truths clear. Mass changes geometry. Geometry changes motion. Geometry changes clock rates. Predictions match experiment. That is enough to build understanding gradually. There is also a quiet philosophical shift hidden here. In Newton's model, space and time existed as passive containers. Matter occupied them. In Einstein's model, space-time interacts with matter. It is dynamic. Stars curve it. Merging black holes disturb it. Expanding cosmology reshapes it. The stage participates in the play. That idea changed not only gravity, but cosmology itself. The universe could expand, contract, evolve. Space was no longer static emptiness. And because time is woven into space-time, cosmic history became part of geometry too. Now return to our original question. Does time move faster in space? General relativity tells us there is no single answer independent of location. Time depends on gravitational environment. Farther from Earth, gravity weakens, so clocks tend to run faster relative to clocks lower down. Near massive objects, clocks run slower. In orbit, this gravitational speeding competes with motion-based slowing from special relativity. So asking whether time is faster in space is like asking whether weather is warmer outdoors. It depends where, when, and under what conditions. Physics prefers details. Still, one broad truth stands: space is not empty background with one universal clock. It is part of a structured, flexible geometry in which time itself can vary. That is a remarkable sentence to exist at all. As the evening grows quieter, imagine Earth drifting through darkness, wrapped not only in atmosphere but in curved space-time. Satellites circle through slightly different geometry. The Moon follows another path. Light from distant stars bends subtly past massive bodies on its long journey to your eyes. Everything moving, timing, curving, and relating. No visible tracks, no giant gears, just geometry deep enough to replace force with form. Now we arrive at one of the most satisfying moments in this whole story. After wandering through Newton, Einstein, motion, gravity, and curved space-time, we can finally answer a practical version of the title question. Do clocks in space run faster than clocks on Earth? For many orbiting clocks, yes, and not because space is magical, not because satellites are closer to the stars, not because vacuum is especially motivating. They run faster for a precise physical reason. They are higher in Earth's gravitational field, and according to general relativity, weaker gravity means faster ticking relative to clocks deeper down. This is one of those statements that still feels backwards the first time you hear it. Gravity is usually introduced as something that pulls, weighs, drags, and resists. Yet here gravity also slows time. The stronger the gravity, the slower clocks run, so Earth's surface, being deeper in Earth's gravitational well than orbit, experiences slightly slower time than many satellites above. Let us build that carefully. Imagine Earth not merely as a ball in space, but as a massive object shaping space-time around it. Closer to Earth's centre, the curvature is stronger. Farther away, it is weaker. Because time is part of space-time, clock rates depend on where the clocks are located in that gravitational landscape. A clock on the ground and a clock far above the atmosphere do not sit in identical temporal conditions. The higher clock gains a small advantage. It ticks faster. That phrase can mislead if taken emotionally. The satellite does not feel hurried. Its onboard systems proceed normally from their own local perspective. Its electronic cycle normally. Its atomic clock counts normally. Everything nearby feels ordinary to itself. The faster only appears when comparing with clocks lower down on Earth. That comparison is everything. Relativity often sounds strange because we instinctively ask which clock is truly correct. The answer is that both clocks are correct locally. They simply trace different circumstances through space-time. Now let's use a simple analogy. Imagine two hikers starting in a valley and then separating. One remains lower, one climbs higher. Air pressure changes with altitude. Temperature may change too. Conditions differ by location. Relativity says timekeeping conditions differ by gravitational altitude. Not metaphorically, operationally. The higher clock accumulates more elapsed time relative to the lower one. Now, Earth's gravity is not so extreme that these differences are dramatic in daily life. If you place a wristwatch on a shelf upstairs, it will not become socially younger than the watch downstairs in any meaningful household dispute. The effect exists, but it is tiny. Tiny enough that ordinary clocks cannot notice. Atomic clocks can. And once precision became good enough, experiments confirmed exactly this prediction. Raise clocks to higher altitudes. Compare them with lower clocks. The higher ones run faster. Move clocks onto mountains. They gain slightly relative to sea level clocks. Put clocks on aircraft. Altitude contributes to faster ticking, while motion contributes slowing, producing a balance depending on speed and route. Physics turns elevators into laboratories. Now let us move from mountaintops to orbit. A satellite circling Earth may be hundreds or thousands of kilometers above the surface. That means it is significantly farther from Earth's center than clocks on the ground. Earth's gravitational pull there is weaker than at the surface. Important note, weaker does not mean absent. People often say astronauts are zero gravity, but that is inaccurate. Gravity in low Earth orbit is still strong. Astronauts float because they are in continuous freefall around Earth, not because gravity disappeared. Still, weaker than surface gravity is enough, and weaker gravity means faster clocks. So if gravity were the only effect, orbiting clocks would gain time relative to Earth clocks. But gravity is not the only effect. Remember Einstein's first shock. Motion slows time. Satellites move quickly. Therefore, their orbital speed creates special relativistic time dilation, tending to slow their clocks relative to Earth. Now we have a contest. Higher altitude speeds clocks up, Higher speed slows clocks down. Which wins? That depends on the orbit. For many navigation satellites, the gravitational speed up is larger than the motion slowdown, so the net result is that clocks in orbit tick faster than clocks on Earth. That is the central answer for this section. Not all space clocks automatically run faster in every scenario, but many orbital clocks do because gravity's effect outweighs velocity's effect. This is especially famous in the global positioning system. GPS satellites orbit much higher than low Earth orbit spacecraft and move at substantial speed. Their clocks gain roughly tens of microseconds per day relative to clocks on Earth after combining both relativistic effects. That sounds small. It is small in daily human terms. It is enormous for navigation. Light travels about 300 meters in 1 microsecond. Timing errors accumulate into position errors rapidly. Without relativistic corrections, GPS locations would drift by kilometers. So engineers must account for faster satellite clocks continuously. This means that when your phone successfully guides you to a restaurant, relativity helped. When it guides you behind the restaurant into a car park, other issues may be involved. Now let's ask a natural question. Why doesn't the satellite itself notice that it is living faster? Because every local observer experiences their own proper time normally. The satellite's onboard clock does not appear abnormal to onboard systems. Its 1 second is 1 second locally. Earth clocks also feel normal locally. The difference emerges only when signals are exchanged or clocks are reunited and compared. This is the recurring rhythm of relativity, local normality, global disagreement. There is something elegant in that. Reality allows everyone their own ordinary experience while refusing to make all experiences identical. Now consider the phrase, higher in the gravitational field. Some people imagine a literal field like invisible fog thick near Earth and thin farther out. That can be a serviceable image, but general relativity describes it more deeply as geometry. Higher clocks occupy regions of different space-time curvature. Their world lines accumulate time differently. If you prefer intuitive language, weaker gravity speeds clocks. If you prefer modern language, space-time geometry differs with altitude. Both point to the same measurable outcome. Now let us compare 3 clocks, one at sea level, one atop a mountain, one aboard a high satellite. The mountain clock runs slightly faster than sea level. The satellite clock often faster still, depending on orbit and velocity balance. This means Earth is surrounded by layers of slightly different timing rates. The universe is not synchronized in neat shells, but there is a gradient. Time changes with height. That sentence remains quietly astonishing. For most of history, people climbed mountains for views, safety, pilgrimage, strategy, or exercise. Few suspected they were also climbing into faster time, not dramatically faster, of course. No one reaches the summit and finds next Tuesday waiting, but measurably faster, and once measured, conceptually irreversible. Now let's talk about low Earth orbit specifically, where spacecraft like the International Space Station travel. Low Earth orbit is relatively close to Earth, so gravity is only modestly weaker than at the surface. But orbital speeds are very high, around several kilometers per second. There, the motion-based slowing can outweigh the gravitational speed-up, meaning clocks aboard may tick slightly slower than clocks on Earth overall. This is a useful reminder. Space is not one condition. Orbit height matters. Speed matters. Mass nearby matters. Asking whether time is faster in space requires specifying where in space and how you move through it. Physics prefers addresses. Now, why should any of this matter emotionally or philosophically? Because it dismantles one of our oldest assumptions, that time is universal background. Instead, even near our own planet, time is layered by environment. Ground floors, mountaintops, aircraft cabins, stations in orbit, navigation satellites, deep space probes, all inhabit slightly different rates of elapsed time. Reality is locally timed. There's also comfort in the scale of it. Though relativity changes clocks everywhere, everyday life remains usable, appointments still function, ovens still preheat, friends still claim they are 5 minutes away in the ancient non-relativistic sense of fiction. The differences are tiny unless precision matters. Yet when precision does matter, nature insists on being obeyed. You cannot negotiate with space-time. Engineers learned this quickly. Another pleasant thought: clocks are historians. A clock's reading tells the story of where it has been, how it moved, and what gravity surrounded it. Two identical clocks separated and reunited become memoirs in numbers. One lived lower, one lived higher, one moved faster, one rested longer. Their disagreement is not error but biography. And because orbiting clocks can run faster than clocks below, the next question becomes practical and unavoidable. How do we keep an entire navigation network working when time itself refuses to stay uniform? There is a lovely irony in modern life. Many people use satellite navigation while rushing somewhere late, and the only reason the navigation works is that engineers took time seriously enough to admit it does not behave uniformly. Every turn-by-turn instruction, every blue dot on a screen, every calm voice saying recalculating depends on one of the strangest facts in physics. Clocks in orbit do not keep the same time as clocks on Earth. If relativity were ignored, the system would fail quickly. So tonight we meet one of the best examples of advanced science becoming ordinary utility. How GPS satellites survive the warping of time. First, what is GPS? Global Positioning System is a constellation of satellites orbiting Earth, each carrying extremely precise atomic clocks. Similar systems also exist, such as Galileo, GLONASS, and Beidou. Your phone or receiver listens to signals from several satellites at once. Each satellite broadcasts the time according to its onboard clock and information about its orbit. The receiver compares arrival times from multiple satellites and calculates distance from each one using a simple idea. Distance equals speed of light, times travel time of the signal. Once distances to enough satellites are known, your position can be triangulated, more precisely trilaterated. So GPS is fundamentally a timing system disguised as a map. That is the key insight. It does not see where you are in the human sense. It infers where you are by measuring when signals arrive. And because radio signals move at light speed, tiny timing errors become large location errors. A 1 microsecond timing error corresponds to roughly 300 meters of distance. 1/1,000,000th of a second. 3 football fields of confusion. So clocks must be extraordinarily accurate. Now let us add relativity. GPS satellites orbit high above Earth, roughly 20,000 kilometers above the surface, moving at several kilometers per second. That means 2 relativistic effects occur simultaneously. First, special relativity. Because the satellites are moving quickly relative to Earth's surface, their clocks run slower than ground clocks. Motion slows time. Second, general relativity. Because the satellites are much farther from Earth's centre, they are in weaker gravity than clocks on the ground. Weaker gravity speeds time. These effects oppose one another. Velocity slows. Altitude speeds. Which wins? For GPS satellites, the gravitational speed up is larger than the motion slowdown, so the net result is that GPS satellite clocks tick faster than clocks on Earth. By about 38 microseconds per day overall approximately. That sounds trivial. It is not. Remember the scale. Light moves fast enough that small time errors accumulate rapidly into navigation errors. If left uncorrected, GPS positions would drift by kilometers per day. Some estimates often cite around 10 kilometers or more of error growth daily. That means your map would steadily become fiction. Restaurants would migrate. Roads would blur. You might be confidently guided into lakes. Relativity prevents this. There is something wonderfully practical about that. A theory involving spacetime curvature now helps people find parking. Now let us ask how engineers solve the problem. They do not wait for satellites to become philosophically comfortable. They correct the clocks. One method is pre-adjustment. The onboard atomic clocks are set to run at a slightly offset frequency on the ground so that once in orbit, under actual relativistic conditions, they tick at the desired rate relative to Earth system time. In simple language, engineers deliberately misset them on Earth so they become right in space. That is a sentence only relativity could make reasonable. Then there are continuous updates. The satellites are monitored by control stations on Earth. Their clock behaviour and orbital positions are tracked constantly. Small deviations from ideal timing are measured, and correction data are uploaded or included in navigation messages. Why so much maintenance? Because relativity is not the only challenge. Real satellites experience temperature changes, electronic drift, tiny orbital perturbations, solar radiation pressure, Earth's imperfect gravity field, and other practical nuisances. The universe supplies elegance. Hardware supplies personality. So GPS timing requires both Einstein and engineering. Now let's understand system time, because users often imagine GPS uses some universal cosmic clock. It does not. GPS uses a defined reference timescale maintained by the system, related closely to atomic time standards. This provides a consistent operational framework for calculations. Remember earlier discussions, there is no universal master clock in nature, so navigation networks create coordinated reference times, useful conventions, carefully maintained, not divine seconds descending from space. This is a beautiful example of human cooperation with physics. Nature gives local clock differences. We build systems to manage them. Now picture what happens when you open a Maps app. Your phone receives signals from multiple satellites. Each signal includes the transmission time according to the satellite's clock. The phone compares those timestamps with its own internal estimate of time and the arrival moments. Because signals travel at finite speed, satellites farther away took longer to reach you. By solving several simultaneous equations using multiple satellites, the device estimates your latitude, your longitude, your altitude, and often a correction to the phone's internal clock. That last part surprises many people. Your phone does not need a perfect atomic clock because the satellite network helps solve timing offsets too. The satellites carry the elite clocks. Your phone brings enthusiasm. Now imagine what would happen if relativity were ignored, but everything else stayed excellent. At first, positions might look acceptable briefly, but as satellite clocks drift relative to Earth reference time, errors would accumulate. The blue dot would slowly wander. Navigation would degrade. Precision applications would fail. Surveying, aviation support, telecommunications timing, financial synchronization, power grids, scientific measurements, all would suffer. GPS is not merely for drivers. Accurate time distribution itself is one of its hidden services. Many infrastructures use satellite timing signals to synchronize systems, so when relativity is corrected in GPS, society quietly benefits in many places users never notice. That is often how successful engineering works, invisible competence. Now let us pause on the deeper lesson. For centuries, time seemed universal enough to trust casually. Then relativity said otherwise. Many might expect such a theory to remain exotic and detached from life. Instead, it became necessary for daily tools. This happens repeatedly in science. Quantum mechanics once sounded abstract. It now underlies electronics. Electromagnetism once seemed theoretical. It powers cities. Relativity once seemed bizarre. It helps you find the supermarket. Reality rewards understanding. There is also something humbling here. Human intuition would not naturally predict that clocks higher above Earth run differently, because gravity changes time. No ordinary sensation reveals it. No one walking outdoors feels the need to apply tensor equations, yet precise instruments expose what senses conceal. The world is richer than instinct reports. Now consider the satellites themselves. They circle Earth in quiet repetition, carrying atomic clocks, broadcasting timing pulses endlessly. No fanfare, no dramatic music, just relentless precision. Somewhere overhead tonight, signals are crossing the sky, passing through atmosphere, entering devices, enabling routes, timestamps, and synchronization. Each signal carries a tiny conversation between relativity and technology. That thought can make the modern world feel more interesting. Even the ordinary is layered with hidden sophistication. Now, a common question. Could we simply design GPS without satellites and avoid relativity? Not with the same global coverage and utility. Any high-precision long-range timing/navigation system involving fast-moving objects at different gravitational potentials must confront relativistic effects. You can ignore relativity only when precision needs are low. GPS precision needs are not low. The universe charges a fee for accuracy. Now let us connect this back to our main theme. Does time move faster in space? GPS gives one of the clearest operational answers. For these satellites, yes, their clocks tend to run faster overall than clocks on Earth once all effects are considered, but they also move fast enough in motion to slow them somewhat. So the true answer is nuanced. Space alone is not the cause. Altitude and speed together determine clock rate. That is physics speaking in full sentences. As evening settles further, imagine Earth below with billions of people living ordinary minutes. Above, a ring of satellites live slightly different minutes, each corrected, monitored, synchronized and trusted. No one on board feels hurried. No one on the ground feels slow. Yet between them, measurable disagreement exists, and civilization quietly depends on managing it well. Once we understand that clocks in orbit and on Earth do not keep identical time, a more human question naturally appears. What is it actually like to live somewhere else? Not in equations, not in a physics lecture, in daily routine. How do astronauts schedule breakfast when the sun keeps appearing every 90 minutes? What time is morning on the moon? How long is a day on Mars? And if humanity journeys far into deep space, what clock would people follow then? These questions sound practical, even domestic, but they sit directly on top of deep physics. Because time away from Earth is never just one thing. There is clock time, body time, planetary daytime, mission control time, relativistic time, psychological time, and occasionally the timeless sensation of searching for a floating pen. Let us begin close to home, aboard the International Space Station. The ISS circles Earth roughly every 90 minutes at an altitude of a few hundred kilometers. That means astronauts aboard see about 16 sunrises and 16 sunsets in a 24-hour Earth day. 16 chances to say, well, that was quick. From the station windows, Earth rolls below in blue curves, city lights, deserts, storms, oceans, auroras, then darkness, then dawn again, then another pass. If your definition of morning is the sun came up, life becomes administratively difficult. So astronauts do not organize their day by visible sunrise cycles. They use scheduled time systems. The ISS commonly operates on coordinated mission time, often aligned with Coordinated Universal Time or UTC. This creates stability. Wake up at a planned hour, exercise at a planned hour, science tasks at a planned hour, meals, maintenance, sleep, communication, all carefully structured. Otherwise the station would become a place where someone announces breakfast every 90 minutes. Now what about relativity on the ISS? The station is higher than Earth's surface, so weaker gravity tends to make clocks run faster than clocks on the ground. But the ISS also moves extremely fast, about 7.7 kilometers per second, and that motion tends to slow clocks. In low Earth orbit, the speed effect slightly outweighs the altitude effect overall, so astronauts aboard the ISS age a tiny bit more slowly than people on Earth. The amount is very small. No astronaut returns looking mysteriously 20 years younger and refusing to explain skincare methods, but measurable differences exist. Even in ordinary orbital missions, time is already personal. Now let us think about what astronauts experience psychologically. Without a natural day-night cycle matching human biology, circadian rhythms can drift. Sleep in space is a real challenge. Lighting schedules, work routines, and environmental controls help maintain a stable pattern. This reminds us that human time is partly astronomical and partly biological. Earth trained our species with a roughly 24-hour rotation. Take humans elsewhere, and clocks become something you manage rather than inherit. Now let's move outward to the Moon. The Moon turns slowly relative to the Sun. A lunar day, meaning sunrise to sunrise at a given location, lasts about 29.5 Earth days. That means roughly 2 weeks of daylight followed by 2 weeks of darkness at many locations. Imagine planning a picnic with that forecast. For future lunar bases, timekeeping becomes a practical challenge. Do settlers use Earth UTC, a lunar local time zone, separate base schedules? Likely mission planners will choose standardized operational systems, perhaps tied to Earth coordination, while also tracking local solar cycles. There are already active discussions among space agencies about lunar time standards because navigation, communication, robotics, and human schedules require precision, and relativity matters there too. The Moon's weaker gravity compared with Earth changes clock rates slightly. Different gravitational environment, different timing behavior, again, tiny for daily sensation, crucial for precision systems. There is something quietly remarkable here. Before permanent lunar cities even exist, humanity already has to ask what time it will be there. Now, onward to Mars. Mars offers one of the most charming timing complications in the solar system. A Martian day, often called a sol, is about 24 hours and 39 minutes. That is close enough to Earth's day to feel familiar, yet different enough to become awkward. If you run a mission from Earth while controlling rovers on Mars, local activity follows Martian daylight. Engineers historically working on rover missions sometimes shifted their own schedules to Mars time, letting their workday drift later each Earth day by about 39 minutes. Imagine your office announcing, "Tomorrow starts 40 minutes later again. Please, adapt." Over time, that rotating schedule becomes exhausting, yet it was practical. Robots on Mars needed commands aligned with Martian mornings, power cycles, temperatures, and operations. This is a wonderful example of another world altering human routines before humans even move there. Mars reached into calendars first. For future settlers, Mars time will become even more personal. Will there be Martian clocks with 24 hours stretched slightly longer? Will people keep sols instead of days? How will birthdays be counted? By Earth years or Mars years? Will meetings begin at 0800 local sol time with the same universal reluctance known across planets? Likely all of the above in some hybrid form. Civilizations are inventive when schedules become inconvenient. Relativistically, Mars has different gravity and different orbital motion than Earth, so precise clock comparisons again differ subtly. Navigation systems around Mars will require careful timing just as Earth systems do. Every world eventually demands clock management. Now let us leave planets entirely and think about deep space missions. Suppose a spacecraft travels between planets slowly by relativistic standards, like current probes. Then special relativistic time dilation is tiny. Mission time is mostly a matter of communication delay and operational scheduling, rather than dramatic aging differences. But communication delay alone becomes a major factor. Radio signals travel at light speed, fast but finite. Earth to Moon, around a second and a bit. Earth to Mars, from a few minutes to over 20 minutes one way depending on orbital positions. Farther outward, much longer. This means real-time conversation gradually disappears with distance. A crew on Mars cannot have natural back-and-forth chats with Earth during many phases. Every exchange becomes correspondence. Question sent, wait, reply, received. This changes social time profoundly. silence stretches between worlds. Now imagine a future relativistic spacecraft travelling at a significant fraction of light speed toward another star. Then special relativity becomes dramatic. Crew members may experience years while more years pass on Earth. Their onboard clocks remain normal locally. Meals happen. Friendships develop. Systems fail at inconvenient moments. Laundry becomes speculative. But when comparing with Earth later, they have crossed unequal time. They would not merely travel through space, they would travel into Earth's future. This makes interstellar migration emotionally complex. A crew departing may know that even a successful return means the home they knew will be gone into history. Technology changed. Generations passed. Languages shifted. Memories archived. The mission clock and the civilization clock diverge. Now let us step back and notice a pattern. On Earth, many people think time means one universal daily rhythm. Sunrise, lunch, afternoon, sunset, sleep. Outside Earth, time fractures into layers. On the ISS, sunrise cycles are too frequent, so schedules are artificial. On the Moon, daylight lasts weeks. On Mars, days are slightly longer. In deep space, communication delay reshapes relationships. At relativistic speed, aging itself diverges from those left behind. So, what time is it becomes several questions at once. What does the clock say? What is the local daylight cycle? What schedule is mission control using? How much proper time has passed for the crew? How delayed is communication from home? That complexity may sound troublesome, but it is also exciting. It means timekeeping becomes part of exploration. Maps are not enough. We must bring calendars, clocks, routines, and social rhythms with us. There is another practical issue future colonies will face: synchronization. If Earth, Moon, and Mars maintain linked economies, science networks, transport windows, and communications, some standard references will be essential. Shared atomic timescales may coordinate systems while local civil times govern daily life, rather like global business now, but with more vacuum. Now let us return briefly to the ISS, because it remains our living laboratory for all this. Astronauts aboard already experience many features of future off-world life: artificial schedules, altered day-night cues, communication with Earth-based teams, different gravity conditions, slight relativistic aging differences, dependence on systems engineering, psychological adaptation to living where ordinary environmental rhythms no longer apply. The ISS is not just a station, it is rehearsal. Every sunrise there, one of 16 before bedtime, previews humanity's future relationship with time. As evening deepens where you are, perhaps Earth outside your window rotates steadily through one familiar night. Somewhere above, astronauts may be seeing another dawn already. Somewhere else, robots on Mars operate on a longer day. The Moon waits through long stretches of sunlight and shadow. Deep probes continue outward under clocks of their own. All these timelines coexist. None cancels the others, each is local truth. And once we begin living beyond Earth, we discover that exporting humans also means exporting schedules, sleep habits, and arguments about punctuality. The cosmos is vast, but some traditions travel well. Now that we've seen how daily life changes across worlds, the next question grows more extreme. What happens to time near the most powerful gravity known in nature, where clocks can slow so much that minutes and years stop resembling one another at all? There are many places in the universe where relativity matters. Satellites feel it. Astronauts feel it through their clocks. Planets and probes require it. But if you want to see Einstein's ideas pushed close to their limits, there is one destination that stands above almost all others: a black hole. Here, gravity is no longer a subtle correction for engineers or a tiny drift in atomic clocks. It becomes dominant, dramatic, and impossible to ignore. Near a black hole, time can slow so strongly relative to distant observers that minutes for one traveller may correspond to years elsewhere. This is the phrase that often captures imaginations. Minutes become years. And unlike many dramatic science headlines, this one rests on real physics. Now we should begin carefully. A black hole is not a cosmic vacuum cleaner roaming hungrily through space, despite popular storytelling. It is a region where matter has collapsed so densely that space-time becomes extremely curved. Gravity near it is so intense that within a certain boundary, called the event horizon, escape to the outside becomes impossible, even for light. Outside that boundary, however, ordinary physics still operates. Objects can orbit. Light can pass nearby. Time can be compared. And this is where gravitational time dilation becomes astonishing. The closer you remain to a massive compact object, the slower your clock runs relative to clocks farther away. We already discussed this gently for Earth. Lower clocks run slower than higher clocks. Near a black hole, the same principle continues, but with far greater strength. Earth gives you tiny differences. A black hole gives you cinematic ones. Now imagine two observers. One remains safely far from the black hole, perhaps aboard a distant spacecraft. Another descends and orbits close to the black hole where gravity is immense. The local traveller feels normal time. Their pulse is normal. Thoughts occur normally. They speak, breathe, blink, and sip coffee at ordinary personal rates, assuming the mission planners made some unusual beverage decisions. Nothing feels frozen to them. But when comparing with the distant observer, the traveller's clock runs much more slowly. That means if 1 hour passes for the traveller near the black hole, much more than 1 hour may pass for the distant observer. Depending on distance and black hole properties, the ratio can become enormous. This is where minutes become years comes from. Not because the traveller senses time dragging, because external time races ahead relative to their local clock. That distinction matters. Relativity never turns your own second into a sluggish personal experience. Your own second always feels like 1 second. The universe saves the strangeness for comparisons. Now let us talk about why black holes are especially powerful. Gravity near Earth is strong enough to keep oceans attached and discourage careless jumping, but Earth is also relatively large. Its mass is spread over a substantial radius. Black holes compress mass into far smaller regions. That means the curvature of space-time near them becomes extreme, and curvature of space-time is what changes clock rates. The tighter the mass concentration, the stronger the effect nearby. This is why a black hole with the same mass as a star can create vastly stronger local relativistic effects than the star itself. Compactness matters. Now, an important subtlety. Not all black holes are equally dangerous in the same way. A small stellar mass black hole has intense tidal forces near the event horizon. The difference in gravity between your feet and head could become fatal long before enjoyable tourism begins. This unpleasant stretching effect is popularly called spaghettification, a word proving scientists occasionally lose restraint. A supermassive black hole, however, such as those found in galactic centres, can have event horizons large enough that tidal forces at the horizon itself may be much gentler. That does not make them holiday resorts, but it changes what close approach might physically permit. For time dilation discussions, supermassive black holes are often the cleaner thought experiment. Now imagine orbiting a supermassive black hole at a stable but close distance. Your local hours proceed normally. Meanwhile, faraway civilizations could experience much longer durations. You might complete a short mission and return to find generations gone. This is relativity's most emotionally dramatic form. Not because you travelled far, because you travelled through unequal time. There is something haunting in that possibility. You leave friends who age rapidly relative to you. You return to descendants, archives, ruins, or myths. Again, this is not fantasy law-breaking. It is gravitational time dilation. Now, many people know this concept through Interstellar, where a planet near a black hole experiences large time differences relative to distant observers. The film consulted physicist Kip Thorne and tried to remain grounded in real relativity, though storytelling naturally adds constraints and drama. The famous idea that 1 hour near the black hole could equal years elsewhere is inspired by legitimate physics, though achieving such exact conditions requires very specific circumstances involving a rapidly spinning black hole and carefully chosen orbit. So the headline version is real in principle, demanding in practice. Now let us ask what the distant observer sees. Suppose you approach the black hole while they watch through telescopes. Because signals from you are increasingly redshifted and delayed, you appear to slow as you near the horizon. Your clock seems to tick more and more slowly. Light from you becomes dimmer and redder. You do not appear to plunge dramatically through the horizon from their viewpoint in simple coordinate descriptions. Instead, you seem to asymptotically slow. Meanwhile, from your own perspective, assuming survival conditions, you cross the horizon in finite proper time without noticing a magical wall there. This mismatch of perspectives is one reason black hole physics fascinates professionals endlessly. Different observers tell different coordinate stories while preserving consistent local laws. Now, does that mean black holes are time machines? Not in the usual fantasy sense. They do not let you travel backward to meet your grandparents and complicate family records. But they can function as one-way future machines. Spend less proper time near a black hole than passes elsewhere, then return. You have effectively leapt forward relative to distant civilization. Relativity permits future asymmetry much more readily than past reversal. Nature seems cautious about backward scheduling. Now, there are practical obstacles large enough to discourage tourism. Radiation from accretion disks around feeding black holes can be lethal. Navigation near strong gravity requires extraordinary precision. Tidal forces can be dangerous. Escape costs energy. Nearby matter may be moving at extreme speeds. Insurance premiums would be uncomfortable. Still, as physics, the principle stands. Near strong gravity, time slows. Near extreme gravity, it can slow enormously. Now let us connect this back to our central question. Does time move faster in space? Near a black hole, the answer becomes a very firm no for the local region compared with distant space. A clock close to the black hole runs slower than one far away. So space does not have one answer. Far from gravity, clocks may run faster relative to Earth. Near extreme gravity, clocks run slower. Location matters completely. This is why asking whether time is faster in space without specifying where is like asking whether water is warm in the ocean. Which ocean? Which depth? Which current? Physics likes details. Now consider the philosophical weight of this. Human beings once imagined time as universal flow. Same river everywhere. Black holes reveal that river metaphor breaks badly. Time is not one global stream. It is local structure shaped by mass and motion. Different regions of the cosmos can experience profoundly different elapsed durations. The universe contains unequal futures. That is an astonishing sentence to exist. There is also a human emotional note here. We often say life is short, near a black hole, whose life and relative to whom becomes less simple. Two people can begin together, separate into different gravitational environments, and reunite having lived different amounts of time. Relativity makes biography frame-sensitive. Now let us be gentle with one final clarification. When we say minutes become years, we mean years elsewhere for the same local minutes. The traveller does not personally experience years packed into minutes like an overbooked calendar. They experience ordinary minutes while distant clocks race ahead. That keeps the concept honest. No one feels compressed centuries in an afternoon, though some meetings come close. After all our talk of flexible clocks, slowed aging, orbital time gains, and black holes turning hours into decades elsewhere, a reasonable listener might now ask a wonderfully grounding question. If time can stretch, slow, speed up, and disagree depending on motion or gravity, why does it still seem to move only one way? Why do we remember yesterday but not tomorrow? Why does spilled tea spread outward instead of leaping neatly back into the cup? Why do eggs scramble more readily than unscramble? Why does childhood become adulthood, but never the reverse? This brings us to one of the deepest ideas in physics, the arrow of time. The phrase does not mean time is a physical arrow flying through the universe with dramatic purpose and excellent posture. It means time has a direction in experience and in many physical processes. Past to future, earlier to later, ordered states tending toward more disordered ones, memory behind us, possibility ahead of us. Even in Einstein's relativity, where different observers measure time differently, this forward character remains stubbornly present. Clocks may disagree on rates, they do not normally run backward. So what creates this arrow? To answer that, we need to meet an old companion of physics, entropy. Now, entropy is often described as disorder, which is useful but incomplete. More precisely, entropy measures how many microscopic arrangements correspond to a larger visible state. That sounds technical, so let us use something friendlier. Imagine a tidy deck of cards sorted by suit and number. There are very few ways to be perfectly sorted. Now shuffle the deck randomly. There are enormously many mixed arrangements. Ordered states are special and rare. Mixed states are common. If you shake the deck repeatedly, it tends toward the common states, not the rare one. Nature often behaves similarly. There are usually many more messy arrangements than neat ones, so systems tend to move from less probable ordered states toward more probable mixed states. That tendency is the heart of the second law of thermodynamics. In an isolated system, entropy tends to increase, and this increasing entropy gives us the most familiar arrow of time. Cream disperses in coffee, heat flows from hot objects to cooler surroundings, ice melts in warm rooms, buildings decay unless maintained. Bedrooms, famously, drift toward chaos unless countermeasures are taken. These processes have a preferred direction. Run them backward, and they look absurdly unnatural. A shattered glass reassembling itself from the floor is not forbidden by microscopic laws in the strictest imaginable sense, but it is so fantastically improbable that you should not schedule around it. Now here is where things become especially interesting. Many fundamental equations of physics are nearly time-symmetric, meaning if you reverse the direction of time in the equations, they can still make sense. Newton's laws, electromagnetism in many contexts, even much of quantum theory can run both ways mathematically. Yet the world we live in has a clear direction. How can reversible laws create irreversible experience? Because macroscopic behavior emerges statistically. Microscopic particles bouncing around may obey reversible equations, but when enormous numbers of them interact, overwhelmingly probable outcomes dominate. It is easy to scramble eggs. It is extraordinarily difficult for countless molecules to spontaneously coordinate themselves back into shell-separated elegance. The arrow comes from probability in large numbers. That alone is a beautiful lesson. Direction can emerge from statistics. Now let us connect this back to relativity. Suppose two observers experience time at different rates due to speed or gravity. One ages less, one ages more. Do they disagree on the direction of time? No. Each still experiences cause before effect locally. Memories still accumulate from earlier states. Entropy still tends to increase in their local systems. A hot drink still cools. Dust still gathers. Emails still multiply. Relativity changes how much time elapses between events, not the everyday direction of processes within local experience. This is crucial. Relativity bends rates and intervals. Entropy gives time its practical forwardness. These are different questions. How fast time passes is not the same as why it feels directional. Now let us consider memory. Why do we remember the past and not the future? Because memory formation itself is a physical process. Your brain stores records of earlier states through biochemical changes. Those records are created after events occur, not before them. The future has not yet produced records in your present brain state. So psychological time aligns with thermodynamic time. We remember lower entropy causes leading to later states, not later states causing earlier memories. That is why nostalgia exists and precognition does not appear in standard daily scheduling. Now another question often arises. Why did the universe begin in a low entropy state at all? Excellent question, still debated. The observable universe appears to have started in conditions that allowed entropy to increase over cosmic history. Without an initially special low entropy beginning, the arrow of time would be much harder to explain. Why the early universe was like that remains one of the great open questions in cosmology. Some proposals involve inflation, gravitational entropy, boundary conditions, multiverse ideas, or deeper unknown principles. Science has good partial maps here, not final closure, which is honest and healthy. Now, gravity complicates entropy in fascinating ways. We often think of clumping matter as more ordered, but gravitating systems behave differently. Under gravity, matter spreading smoothly can actually represent lower gravitational entropy than matter collapsing into stars, galaxies, and black holes. Black holes themselves possess enormous entropy, as discovered through the work of Jacob Bekenstein and Stephen Hawking. So gravity is not just shaping clocks, it also participates in the universe's thermodynamic story. The cosmos is wonderfully efficient at making topics overlap. Now think about daily life. When you bake bread, chemical reactions proceed in one direction under heat. When autumn leaves decay, biological order breaks down and recycles. When you age, cells accumulate changes over time. Living organisms maintain local order by consuming energy and exporting entropy into surroundings. That is how life resists disorder temporarily without violating thermodynamics. We tidy rooms by increasing disorder elsewhere, often in the form of metabolic effort and mild frustration. So life is not an exception to the arrow of time. Life is a participant in it. Now let us address a common misunderstanding. People sometimes say, if time is the fourth dimension, why can't we move backward in it like walking backward in a hallway? Because dimensions in mathematics need not behave identically. Time in relativity has a different structural role than space, tied to causality and light cones. Also, the thermodynamic arrow strongly distinguishes usable forward progression in physical processes. You can turn around in space. Turning around in time is not comparably available. Spacetime geometry is not a hotel corridor. Now consider movies played backward. Smoke returns to cigarettes. Rain leaps upward. Broken plates assemble. People instantly recognize the reversal. How? Because we are deeply trained by entropy. We know what ordinary forward processes look like. Our brains are arrow detectors. Even children notice when physics looks backward. That is a remarkable cognitive fact. Now let us bring in relativity one more time. Suppose an astronaut near a black hole experiences 1 hour while Earth experiences years. Does Earth's arrow run faster? Not exactly. Each region follows its own local processes with the same directional character. Entropy increases locally in both places. What differs is how much proper time each accumulates between comparison events. The arrows still point forward. Their clocks simply cover unequal distances along them. That image is useful. Relativity changes scale, not orientation. Now there are some subtle physical processes involving particle interactions that violate certain symmetries and raise deep questions about time reversal, especially in weak interactions. These are important in high-energy physics, but they do not overturn the ordinary thermodynamic arrow governing cups, kitchens, aging, and evenings. Your spilled cereal is not waiting on CP violation theory to re-enter the bowl. Now let us step back. We began this journey asking whether time moves faster in space. We discovered that rates vary with motion and gravity. Yet despite all that flexibility, one truth remains familiar. Processes still unfold from earlier to later. You can have slower time. You can have faster time relative to elsewhere. You can have different clocks disagreeing honestly, but you still cannot untoast toast. There is comfort in that consistency. The universe may be subtle, but it is not arbitrary. As the night grows quieter, think of time not as a river rushing universally forward, but as many local clocks tracing different paths, while entropy gives events their common direction. Different speeds, different rates, shared forwardness. That may be the most balanced picture yet. After hearing that motion changes time, gravity changes time, satellites need relativistic corrections, and black holes can separate hours from years, many people arrive at an understandable conclusion. Surely daily life should feel stranger than this. If relativity is real, why does breakfast happen normally? Why does walking to the shop not noticeably change your age? Why do clocks on the wall mostly agree? Why does no one return from a motorway trip dramatically younger than the neighbours? Why does your coffee cool according to familiar annoyance rather than space-time drama? This is an excellent question, because it highlights something fundamental about physics. Many profound laws are always active, yet only become obvious under certain scales. Relativity is one of them. Humans barely notice relativity in everyday life, because the conditions of ordinary life are mild. Our speeds are slow compared with the speed of light. Our gravitational differences are small compared with stronger cosmic environments. Our clocks are usually not precise enough to reveal tiny discrepancies directly. So relativity is present, but quiet. It is happening all the time, but in whispers. Let us begin with speed. Special relativity becomes significant when velocities approach the speed of light, commonly written as c. That speed is about 300,000 kilometers per second, a very large number. So large that ordinary human motion is tiny by comparison. Walking speed might be a few kilometers per hour. A car on a highway perhaps around 100 kilometers per hour. A commercial jet perhaps around 900 kilometers per hour. Even fast spacecraft in Earth orbit move only a small fraction of light speed. These are impressive by human standards. They are modest by relativistic standards. This is why time dilation from everyday movement is incredibly small. If you walk across a room, your clock does run differently relative to a stationary chair, but by such a tiny amount that the universe itself seems embarrassed to mention it. No biological effect could be noticed. No birthday plans need adjustment. No family member must say, "You took the stairs and now you're younger." The same applies to driving. A commuter travelling daily at road speeds experiences motion-based time dilation, but it is unimaginably small. Real in principle, negligible in life. This is common in physics. An effect can be true, measurable with enough precision, and irrelevant to ordinary sensation simultaneously. Now let us consider gravity. General relativity says clocks lower in stronger gravity run more slowly than clocks higher up. That means a person at sea level and a person on a mountain age at slightly different rates. Again, real. Again, tiny. Earth's gravity is strong enough to keep us grounded and humble, but not so extreme that everyday altitude differences create dramatic temporal consequences. If you move from ground floor to rooftop, you do not leap into the future. If you spend a weekend hiking, you do not return requiring chronological reintroduction. Yet with atomic clocks, these differences can be measured. That is the recurring pattern. Too small for senses, large enough for instruments. Now think about clocks themselves. Most household clocks are not precision scientific devices. They drift for ordinary reasons: temperature, battery condition, manufacturing tolerances, quartz stability, user neglect, decorative optimism. Those imperfections are vastly larger than tiny local relativistic differences in many daily contexts. So when two kitchen clocks disagree, Relativity is almost never the culprit, though it would be charming if it were. Usually one simply needed setting months ago. Modern precision systems, however, do notice relativity. Satellite clocks, laboratory clocks, network timing systems, geodesy instruments, particle experiments, and navigation infrastructure all require corrections or understanding rooted in Einstein's theories. So humanity as a civilization notices relativity even when individuals do not. Your body may ignore it, your smartphone quietly does not. Now let us use a useful analogy. Imagine ocean tides. The gravitational pull of the moon influences oceans constantly. But if you stare at one glass of water for 30 seconds, you do not watch tides happening dramatically. The effect is real, but subtle at your scale. Relativity in daily life is similar, always there. Usually small, visible when viewed with the right tools, scales, or accumulated precision. Now consider another reason relativity feels hidden. Your own local time always feels normal. This is crucial. If you are moving, your watch ticks normally to you. Your heartbeat feels normal. Thoughts arrive at normal pace. Lunch hunger appears on schedule. If gravity changes your clock rate relative to someone elsewhere, you do not feel slowed or sped. Everything around you changes together locally. Differences emerge only when comparing separated clocks or signals. That means subjective experience protects everyday intuition. You never wake up thinking, my proper time feels slightly Lorentz adjusted. Local normality masks global difference. This is one of Einstein's deepest gifts to confusion. Now let us discuss evolution, because our intuitions did not arise in a physics classroom. Human perception evolved for survival in moderate environments. We needed to detect predators, judge distances, coordinate with groups, throw objects, track seasons, and remember where food was. We did not need to sense nanoseconds of time dilation. We did not need instinctive understanding of four-dimensional spacetime curvature. Natural selection rewards usefulness, not cosmic completeness. So there is no shame in relativity feeling counterintuitive. Your ancestors were solving different exams. Now consider aviation. Aircraft travel faster and higher than daily ground life. So relativistic effects become larger, though still small. Precision clocks flown on airplanes can detect timing differences relative to clocks left behind. Passengers themselves notice jet lag, but jet lag is biological schedule disruption, not direct awareness of relativistic time dilation. One is circadian confusion, the other is space-time geometry. They often travel together socially while being scientifically distinct. Now think about the International Space Station. Astronauts orbit Earth rapidly, so special relativity slows their clock somewhat. Their higher altitude weakens gravity, which speeds clocks somewhat. The net result depends on orbit specifics, but differences accumulate measurably over time. Astronauts still do not feel relativity happening. They feel workload, floating, exercise routines, scientific tasks, homesickness, and probably occasional concern about drifting pens. Again, local experience remains ordinary. Now let's address a common misunderstanding. Some people imagine relativity should create bizarre visible distortions constantly if true. But physics often contains effects that only dominate under specific extremes. Quantum mechanics governs atoms, yet chairs still look like chairs. Relativity governs space-time, yet city buses still mostly follow schedules for non-cosmic reasons. Large-scale ordinary life emerges smoothly because limits simplify behavior. At low speed and weak gravity, relativity reduces approximately to Newtonian expectations. That is why Newtonian mechanics remained successful for centuries. It is an excellent approximation where humans naturally live. The same is true in many sciences. Simple rules can be locally valid approximations of deeper rules. Now consider how often we already rely on hidden corrections. Phones synchronize time through networks. financial systems timestamp transactions, power grids coordinate frequency, navigation uses satellites, scientific labs compare clocks globally. All these systems must care about precision beyond human sensation. Civilization extends perception through instruments. That is why Einstein matters more now than in 1905. Technology entered scales where tiny effects became practical. Now let us imagine if the speed of light were much lower than it is. Then everyday driving might produce visible time dilation. Cyclists could return slightly younger from errands. Train schedules would require relativistic notices. Sports records would become chronological negotiations. Fortunately or unfortunately, nature chose a very high light speed. This gives ordinary life a wide, comfortable zone where classical intuition works. The universe is exotic at extremes, practical at breakfast. Now gravity too could have been different. If Earth were compressed into a much denser object, with the same surface access somehow available, gravitational time dilation near daily life might be obvious. Clocks upstairs and downstairs could differ dramatically, but Earth is comparatively gentle on relativistic scales, so daily life remains stable enough to be boring in the best sense. Now let us reflect on measurement. The fact that humans barely notice relativity does not make it less real. We do not directly sense radio waves either. We do not see bacteria unaided. We do not feel continental drift moment by moment. Reality is under no obligation to match our sensory bandwidth. Science exists partly because senses are narrow. Tools widen them. Atomic clocks widened time perception. Telescopes widened spatial perception. Particle detectors widened matter perception. Relativity became visible when measurement matured. Now perhaps there is comfort here. The universe can be profound without being disruptive. You need not compute Lorentz factors to enjoy dinner. You need not solve Einstein field equations to cross a street safely. Truth can operate beneath awareness while life remains livable. That is generous design, if one likes that word. Now, return to our original theme. Does time move faster in space? Yes, sometimes relative to Earth clocks depending on altitude and speed. Does motion slow aging? Yes, measurably under the right conditions. Does gravity alter clocks? Yes, constantly. Why don't humans notice? Because our bodies live in a calm corner of parameter space. Slow speeds. Moderate gravity, short distances, imprecise senses, shared environments. Relativity becomes spectacular only when we leave the comfort zone, and perhaps that itself is a lesson. Many truths wait quietly outside ordinary scale. As evening settles deeper, imagine yourself standing still in a room. Earth rotates beneath you, orbits the sun, moves through the galaxy, while space-time curves gently under your feet. Tiny relativistic differences exist between floor and ceiling, between you and satellites overhead, between sea level and mountains far away. Yet your lamp glows, your breath slows, the room feels stable. Reality can be astonishingly complex while appearing calm. We began with a simple question. Does time move faster in space? By now the answer is both yes and no, depending on altitude, speed, gravity, and the path a clock takes through the universe. But after all the satellites, spacecraft, black holes and atomic clocks, a deeper question quietly remains. What does any of this mean about reality itself? Because once time stops being universal, many assumptions we barely notice begin to loosen. The floor beneath ordinary thought shifts a little, and that can be unsettling at first. Then, often, it becomes beautiful. For most of human history, time felt absolute. Morning followed night, children became adults, seeds became trees, the old became older. Days passed for everyone alike, or so it seemed. There might be different calendars, different time zones, different clocks, but underneath all of them we imagined one shared river flowing steadily forward. Einstein changed that, not by removing time, by localizing it. Time became something measured along paths, affected by motion and gravity, rather than imposed identically everywhere. That is a profound philosophical change. It means reality is less like a single synchronized broadcast and more like a network of local experiences connected by lawful relationships. No universal master clock, no single cosmic now, many valid local times, one structured universe. That is a richer picture than the old one. Now let us consider what disappears first, the universal present. In everyday language, we casually ask what is happening right now on the far side of the galaxy. It sounds harmless. But relativity tells us right now across great distances is not absolute. Different observers moving differently can slice space-time into present moments differently. There is no observer-independent cosmic now spanning all space. That does not mean chaos. It means simultaneity is frame-dependent. This is difficult only because our brains evolved in villages, not galaxies. Across a town shared now works well enough. Across interstellar distances, nature asks for more precision. So one lesson of faster time and space is this: the present is local. That sentence alone changes many intuitions. Now let us look at identity. If two twins separate and reunite with different ages because one travelled fast or near strong gravity, then personal history depends partly on route. Your life is not merely what happens, it is also the path through space-time along which it happens. That sounds dramatic, but it is physically plain. A clock records biography through elapsed time, so do bodies. Two people beginning together can honestly live different durations before meeting again. Reality permits unequal aging without contradiction. That means duration is not a universal possession. It is path-dependent. There is humility in that. Now think about location. We often treat place and time as separate categories. Where are you? What time is it? Relativity merges these more deeply. An event is not fully described by place alone or time alone, but by space-time coordinates and relations to observers. You are somewhere and someone together. That may sound obvious linguistically, but scientifically it means space and time are not isolated bookkeeping systems. They are woven. Mass curves that woven structure. Motion changes measured intervals within it. The universe is geometric in ways common sense never requested. Now let us consider causality, one of the great stabilizers. Even though observers disagree on rates and simultaneity, relativity preserves causal structure. Causes precede effects within allowable signal limits. Information does not casually outrun light to create nonsense in ordinary theory. This is important. Reality did not become arbitrary when time lost universality. It became subtler while keeping order. That distinction matters emotionally as much as scientifically. Many people fear that if old certainties fall, then everything dissolves. Physics often shows the opposite. Naive certainty falls, deeper consistency appears. Now there is another philosophical implication. If different observers each measure legitimate times, then perspective matters objectively. Not anything goes perspective, not mere opinion, structured perspective. Your measurements depend on motion and gravity, yet transform lawfully into others' measurements. This is one of relativity's most mature lessons. Context matters without destroying truth. That idea reaches beyond physics, though we should not abuse metaphors too aggressively. Still, it is striking that nature herself uses perspective carefully rather than absolutism crudely. Now let us discuss the block universe, because it often appears whenever relativity enters thoughtful rooms. Some philosophers and physicists interpret relativity as suggesting all events in space-time simply exist within a four-dimensional structure, with past, present and future laid out differently than our flowing intuition suggests. This is sometimes called eternalism or the block universe view. Under that interpretation, time does not flow objectively. Rather, conscious beings experience sequences along world lines. Others resist this framing or modify it. the debate continues. What matters here is not choosing sides before sleep. What matters is recognizing that relativity reopened ancient questions about whether time truly passes or whether passing is partly experiential. That is no small consequence for a theory born from light signals and train thought experiments. Now bring back our title phrase, faster time in space. When clocks higher above Earth tick faster than clocks below, reality is telling us that duration is not uniform substance, poured evenly everywhere. Time is responsive, it depends on structure. Gravity changes it, motion changes it, paths change it. This suggests the universe is relational at a deep level. Properties often emerge through comparisons, not isolated absolutes. That theme appears elsewhere in modern physics too. Now consider human psychology. We feel trapped by clocks sometimes. Deadlines, aging, schedules, waiting rooms, delayed messages, taxes, forgotten birthdays. Time can seem like an external tyrant. Relativity softens that image. Time is not one tyrant reigning equally over all. It is a feature of the physical world interacting with circumstances. That does not make deadlines vanish, regrettably. But it changes the metaphor. We do not live under one giant clock. We inhabit many local rhythms, biological rhythms, planetary rotations, orbital periods, atomic transitions, personal histories, relativistic durations. Reality is layered timing. Now there is also beauty in scale. At human speeds, relativity hides. At orbital scales, it matters practically. At near-light speeds, it transforms travel. Near black holes, it becomes dramatic. This means truths can be gentle in one regime and powerful in another. A single law spans kitchen counters and galactic centers. That unity is one of science's quiet miracles. Now let us ask whether faster time in space diminishes human significance. I would argue the opposite. That we can discover such truths at all is extraordinary. Creatures on one small planet, evolved from earlier life, built clocks precise enough to notice that mountaintops age differently than valleys and satellites disagree with sidewalks. That is astonishing. The universe became strange, and we understood some of it. There is dignity in that. Now another consequence concerns future civilization. As humans spread to the Moon, Mars, orbital habitats, and perhaps beyond, time differences will move from philosophical curiosities to daily logistics. Families on different worlds may age at slightly different rates. Messages may travel with long delays. Shared calendars may fragment. See you next year may require careful definitions. Human culture will adapt to relativistic plurality. The future may normalize what once sounded impossible. Now let us be careful not to exaggerate. Most relativistic differences near planets are tiny. Mars settlers will not become legends in a weekend through time dilation, but the conceptual shift matters more than the magnitude. Once time is not universal, civilization must choose conventions consciously. That is a mature stage of understanding. Now think of memory. You remember your past not because the universe handed you a universal clock, but because physical processes in your brain recorded earlier states along your path. Your life is a world line with memory. Others have theirs. We meet, separate, reunite, exchange stories, synchronize loosely, drift again. That is human existence in relativistic language. Less romantic perhaps, but strangely tender. Now there is one final comfort. Even though time is flexible, your immediate life remains real and coherent. Local experience is not invalidated by cosmic subtlety. The tea still warms your hands, conversations still matter, kindness still arrives in sequence. Music still unfolds note by note. Sleep still comes 1 minute at a time. Relativity does not erase intimacy, it situates it. Your moment is local, but no less meaningful for that. Imagine billions of clocks across Earth, satellites overhead, probes between planets, stars orbiting galactic centers, and perhaps distant civilizations keeping calendars under other skies. None share one universal now. All inhabit one lawful cosmos. Different rates, different paths, different histories, connected reality. And perhaps that is what faster time in space means most deeply. The universe is not simpler than we hoped. It is more connected, more contextual, and more elegant than we first imagined. We began tonight with a question so ordinary it could be asked over tea, on a late walk, or while looking absent-mindedly at the stars. Does time move faster in space? At first, it sounds like a simple yes or no puzzle. Something for trivia night. Something to ask before sleep and forget by morning. Yet the deeper we followed it, the more it opened. We found that time is not one universal river flowing equally for all things. We found that motion changes clocks, gravity changes clocks, altitude changes clocks, speed changes clocks, paths through space-time change clocks. Two honest clocks can disagree. Two twins can reunite at different ages. A satellite can live slightly faster minutes than the ground below. A traveller near a black hole could return to a future they barely touch personally. All of this from one humble question. That is often how science works. You open one small door and discover an entire landscape behind it. Now perhaps the most comforting truth in all of this is that your own moment remains steady to you. Your heartbeat still feels like your heartbeat. Breathing remains familiar. A warm blanket remains warm. Thoughts arrive one after another in gentle sequence. No one lies awake sensing nanoseconds of gravitational difference between pillow and floor. Reality is stranger than intuition, but not cruelly so. It lets us live locally while being globally astonishing. That is a kind arrangement. Tonight, somewhere above you, clocks are already disagreeing with the one beside your bed. Aboard the International Space Station, time is accumulating differently than it is in your room. Inside navigation satellites circling silently overhead, atomic clocks are being corrected because Earth and orbit do not share identical rates. On mountaintops, clocks gain tiny amounts relative to valleys. Farther out, probes moving through the dark carry their own histories in numbers. Elsewhere in the universe, stars orbit dense remnants, galaxies rotate, and perhaps on worlds we've never seen, someone may also be asking what time really is. And their answer would depend on where they stand. There is something peaceful in knowing the universe does not insist on one schedule. It allows many local rhythms, the turning of planets, the pulsing of atoms, the beating of hearts, the cycles of sleep, the long timing of mountains eroding, the quick timing of meteors burning bright for seconds, the patient timing of stars living for billions of years, all real, all local, all part of one connected cosmos. Perhaps that is what makes time feel so personal. It is not merely numbers on devices, it is the measure of change where you are, the story your path tells, the record of moments gathered by one particular life. And though relativity reveals that others may gather moments at different rates, it does not reduce the value of yours. A minute of comfort is still a minute of comfort. An hour of laughter remains an hour well spent. A quiet evening remains quietly precious. Physics can stretch clocks. It does not shrink meaning. Now, as this journey draws softly toward rest, imagine Earth beneath a night sky turning through space. Cities glowing, oceans shifting, clouds drifting, satellites tracing invisible arcs, clocks in laboratories ticking, clocks in kitchens ticking, clocks in wrists, towers, stations, servers, observatories, and distant spacecraft ticking, none perfectly alike, all faithful to their own place. And somewhere above us, another clock is ticking differently tonight. Not wrongly, not mysteriously, just according to the deeper rules of reality. So if your eyes are growing heavy now, and the room has become quieter than it was when we began, you can let that thought settle beside you. The universe is vast, time is flexible, your moment is real, and for now, here in your small corner of space-time, it may simply be time to sleep,